Imagine something so thin that it's a billion times smaller than an atom, yet so powerful that it could warp the very fabric of space-time. A structure so extreme that if one were to pass through our solar system, it could disrupt the orbits of planets without even touching them. Scientists call these things cosmic strings, and if they exist, they might be the key to some of the biggest mysteries in the universe. But what exactly are they? And if they're out there, could they be shaping reality in ways we don't even understand yet? Let's start at the very beginning, the birth of the universe itself. Right after the Big Bang, the universe was an unimaginably hot, chaotic place. Energy and matter were crammed together in ways that don't happen anywhere today. But as things expanded and cooled, fundamental forces began to separate: gravity, electromagnetism, and the forces that hold atoms together all broke apart from a single unified force. According to some theories, this process wasn't perfectly smooth. Cracks may have formed in the fabric of space-time itself. These cracks are what we now call topological defects, and one of the most extreme versions of these defects is the cosmic string. Picture space-time as a perfectly smooth sheet. If you twist or tangle it, you get tiny imperfections, defects that never go away. Cosmic strings are thought to be one-dimensional versions of these defects, infinitely thin but incredibly dense, like cosmic scars left behind from the earliest moments of existence. And here's where it gets even weirder. These strings aren't just sitting there. They move at nearly the speed of light, stretching across the universe like invisible threads, distorting space and time as they go. But here's the real mind-bender. Cosmic strings might be older than everything we know. If they exist, they could have formed a fraction of a second after the Big Bang, meaning they've been around for over 13.8 billion years. They could be relics from a time before galaxies, before stars, even before atoms existed. And if that's true, they might still be out there, shaping the universe in ways we don't yet understand. Now you might be wondering, if these things are so powerful, why haven't we seen them? Wouldn't a gigantic, universe-spanning structure be obvious? The answer is tricky. Cosmic strings don't emit light, they don't reflect anything, and they don't interact with normal matter in ways we can easily detect. But they do have mass. And because mass bends space-time, a passing cosmic string could warp light from distant stars, creating strange distortions known as gravitational lensing. Scientists have spent decades searching for these warps, hoping to spot a cosmic string in action. And while there have been some intriguing hints, no one has found solid proof, yet. But if they do exist, they could explain some of the biggest cosmic mysteries out there, including the formation of galaxies, the structure of dark matter, and maybe even the true nature of the universe itself. But here's where things get even wilder. If cosmic strings exist, they could be more than just passive relics. Some theories suggest they might still be connected to the fundamental forces of the universe, meaning they might still be shaping reality. Some even speculate that these strings could be linked to parallel universes. If that's true, then finding one wouldn't just confirm a long-standing theory. It could change our entire understanding of what's possible in physics. And this is just the beginning. Because the more we learn about cosmic strings, the more questions we uncover. Could they be responsible for some of the unexplained gravitational anomalies we see in deep space? Could they provide a link between quantum mechanics and general relativity, finally solving one of the biggest problems in modern physics? Could they even be used to create wormholes, shortcuts through space and time? Let's dive deeper into what we know so far, what scientists are doing to search for them, and what it would mean for humanity if we ever found one. To truly understand the potential impact of cosmic strings, we need to dig deeper into their physical properties. The first thing to know is that cosmic strings are not like the strings you might imagine from everyday life. They aren't made of atoms, nor are they simple filaments floating through space. Instead, they are believed to be infinitely thin but infinitely long, meaning they stretch across vast distances while remaining unimaginably small in width. Some models even suggest they could wrap around the entire universe multiple times. But despite their extreme thinness, cosmic strings carry an enormous amount of energy. In fact, a cosmic string just 1 kilometer long would have more mass than an entire planet. This density is what makes them so powerful. Wherever a cosmic string moves, it warps the very fabric of spacetime around it, creating gravitational disturbances that could have influenced the way the universe evolved. Now, let's talk about how cosmic strings move. Since they formed in the earliest moments of the universe, they don't just sit still. They are constantly moving at relativistic speeds, meaning they travel close to the speed of light. As they whip around the cosmos, they sometimes form loops, which can eventually shrink and disappear, releasing energy in the form of gravitational waves. This means that if cosmic strings exist, they should be producing ripples in spacetime that we might be able to detect with the right instruments. And this brings us to one of the most exciting aspects of the search for cosmic strings: gravitational wave detection. In recent years, scientists have made groundbreaking discoveries by detecting gravitational waves, which are ripples in spacetime caused by massive objects like merging black holes or neutron stars. But if cosmic strings exist, they might be generating their own unique patterns of gravitational waves. Some researchers believe that certain unexplained signals picked up by observatories like LIGO and Virgo could already be evidence of cosmic strings in action. But there's another way we might find them: gravitational lensing. When light from distant galaxies or quasars passes near a massive object, it bends, creating distorted or duplicated images. If a cosmic string were to pass in front of a distant light source, it could create a sudden, sharp gravitational lensing effect, a telltale sign of its presence. Some astronomers have searched for these effects in deep space surveys, and while a few unusual lensing events have been recorded, none have yet been confirmed as evidence of a cosmic string. So if cosmic strings are out there, where are they now? Are they hiding in the vastness of space, too rare to easily find? Or is it possible that they never formed at all? Scientists have run massive computer simulations of the early universe to predict how cosmic strings would have behaved, and the results suggest that if they exist, they should still be out there today, stretched across cosmic distances. But spotting them requires either direct observation of their gravitational effects or indirect detection through gravitational waves, both of which are incredibly difficult to measure. But here's the most mind-blowing part: if cosmic strings exist, they might be the missing link in understanding the structure of the universe itself. Some theories suggest that these strings could have played a crucial role in forming the cosmic web, the vast, interconnected structure of galaxies and galaxy clusters we see today. Imagine the universe as a vast three-dimensional spiderweb, with filaments stretching between galaxies like invisible threads. Some physicists propose that these filaments might have formed along the paths of ancient cosmic strings, meaning that these mysterious structures could have shaped the very galaxies we live in. And then there's the possibility that cosmic strings could be linked to dark matter, the mysterious, invisible substance that makes up about 85% of the matter in the universe. Some scientists speculate that cosmic strings might be tied to exotic particles that interact only through gravity, providing a potential explanation for why we can't see dark matter directly. If this idea is true, then finding a cosmic string wouldn't just confirm their existence, it could solve one of the greatest mysteries in all of physics. But we're just scratching the surface. What if cosmic strings are more than just remnants of the early universe? What if they are still actively shaping reality in ways we haven't even considered yet? Some radical theories suggest that cosmic strings could be connected to higher dimensions, acting as cosmic bridges between different parts of spacetime. If that's true, then they might hold the key to understanding concepts like wormholes, shortcuts through space that could allow faster-than-light travel. And it gets even crazier. Some physicists have proposed that cosmic strings could be linked to parallel universes. The idea is that if the universe underwent multiple phase transitions in its early moments, different regions of spacetime could have evolved in different ways. Cosmic strings might be the boundaries between these regions, meaning that if we ever found one, it might provide a literal doorway to another reality. At this point, the search for cosmic strings isn't just about confirming a theory, it's about rewriting our understanding of the universe itself. If they exist, they could answer some of the deepest questions about space, time, and reality. And if they don't? Then we'll have to rethink our models of the early universe and what really happened in those first few moments after the Big Bang. But one thing is certain: the mystery of cosmic strings isn't going away anytime soon. The more we look, the more we realize how little we know. And maybe, just maybe, somewhere out there in the vastness of space, a cosmic string is drifting silently through the void, waiting to be discovered. If cosmic strings are out there, then the implications are staggering. These infinitely long, unimaginably thin defects in space-time wouldn't just be leftovers from the universe's birth. They would still be influencing reality right now. And if they move at near light speeds, that means they could be crossing the universe at this very moment, warping the space around them as they go. But what exactly would that look like? If a cosmic string were to pass through our solar system, would we even know it? The answer is both fascinating and terrifying. Unlike a black hole or a massive object with strong gravity, a cosmic string wouldn't pull things toward it. Instead, it would create a bizarre, almost sci-fi-like distortion. Imagine looking at a star in the night sky, only for it to suddenly split into two identical images. This is one of the most well-known predicted effects of a cosmic string. If light from a distant source passes near one, it wouldn't bend in the traditional sense but would instead be duplicated due to the way space-time is warped around the string. This effect is called conical space-time. Normally, space-time is smooth and continuous, but if you introduce a cosmic string into the equation, it creates a deficit angle, essentially a missing chunk of space. Any object that passes near a cosmic string would experience this distortion, meaning that if we ever manage to observe a sudden, perfect duplication of a celestial object with no other explanation, it could be our first direct evidence of a cosmic string. But that's not all. Because cosmic strings carry an enormous amount of energy, they also produce something known as gravitational radiation. This means that as they vibrate, oscillate, or form loops, they send ripples through space-time, gravitational waves that could, in theory, be detected by observatories like LIGO and Virgo. Scientists have already detected gravitational waves from colliding black holes and neutron stars. But if they were to find an unusual pattern of gravitational waves that didn't match these known events, it could be a sign that a cosmic string is nearby. So if cosmic strings are so influential, why haven't we detected them yet? The answer comes down to just how subtle and elusive their effects are. They don't emit light, they don't interact with normal matter in the way stars and planets do, and they move so fast that any observable effects they create might last for only a fraction of a second. That means spotting a cosmic string would require incredibly precise measurements of gravitational waves, light distortions, and cosmic background radiation. And speaking of the cosmic background radiation, there's another potential clue hidden in the oldest light in the universe. The cosmic microwave background (CMB) is the afterglow of the Big Bang, a faint radiation that fills the entire universe. Scientists have studied it in incredible detail, mapping tiny temperature fluctuations that reveal how the early universe evolved. If cosmic strings exist, they should have left scars in this background radiation, subtle but detectable patterns that show where space-time was warped in the past. Some researchers believe that slight anomalies in the CMB might already hint at the presence of cosmic strings, but the evidence isn't yet strong enough to be definitive. Future missions, like the European Space Agency's planned CMB studies, could provide the higher resolution data needed to settle the question once and for all. But what if we don't just detect a cosmic string? What if we find one up close? What would happen if a cosmic string passed near Earth? While it wouldn't pull us in like a black hole, it would still have an effect. For one, it could cause minor distortions in GPS signals and satellite communications due to the way it warps spacetime. If a particularly large loop were to oscillate near our planet, it might even create measurable fluctuations in Earth's gravitational field, something sensitive instruments might be able to pick up. And here's where things take an even more mind-bending turn. If cosmic strings are connected to fundamental forces in the universe, could we ever harness their energy? Some theoretical physicists have speculated that cosmic strings could contain immense amounts of trapped energy, far more than anything we could ever generate with nuclear power. If humanity were somehow able to interact with a cosmic string, it could, in theory, be the most powerful energy source imaginable. But even more fascinating is the idea that cosmic strings might provide a gateway to faster-than-light travel. Because they stretch across vast distances and warp spacetime around them, some have speculated that if 2 points on a cosmic string were somehow connected, it might create a shortcut through space, essentially a naturally occurring wormhole. If this idea holds any weight, it means that finding a cosmic string wouldn't just be a scientific breakthrough, it could be the first step toward interstellar travel. And yet, despite all these possibilities, cosmic strings remain one of the most elusive concepts in modern physics. Every new study, every new observation, seems to bring more questions than answers. Are they rare? Are they hiding in deep space, beyond our current ability to detect? Or is it possible that they never formed at all, and our theories about them are simply wrong? The search continues, and with every new discovery in gravitational wave astronomy, dark matter research, and cosmic background studies, we move closer to an answer. If we do find them, they could redefine our understanding of the universe in ways we can't even imagine. And if we don't, then we'll have to rethink one of the most fascinating ideas ever proposed about the structure of reality. If cosmic strings do exist, then they might be among the oldest structures in the universe, remnants of an era before galaxies, before stars, before even atoms had fully formed. That's what makes them so compelling. Unlike other celestial objects that evolve over time, cosmic strings would have remained largely unchanged since their formation in the early universe. They would still be out there, stretching across the cosmos, influencing space-time in ways we have yet to fully understand. One of the most fascinating aspects of cosmic strings is their potential connection to inflation, the rapid expansion of the universe that occurred just fractions of a second after the Big Bang. According to some theories, cosmic strings could have formed as the universe cooled and fundamental forces separated. This process, known as spontaneous symmetry breaking, is similar to how cracks form in ice as water freezes, except, in this case, the cracks would be defects in spacetime itself. If true, that would mean cosmic strings are relics from the very fabric of the cosmos, possibly containing information about the universe's earliest moments. Some researchers have even suggested that studying cosmic strings could help us understand grand unified theories, attempts to unify the fundamental forces of nature. If cosmic strings formed during phase transitions in the early universe, they could provide evidence for how forces like electromagnetism, the weak nuclear force, and the strong nuclear force were once connected before splitting into what we observe today. But here's where things get even stranger. Some theories suggest that cosmic strings could also be linked to dark matter. Dark matter is one of the biggest mysteries in astrophysics, an invisible substance that makes up most of the universe's mass but doesn't interact with light. Some physicists propose that cosmic strings could act as seeds for dark matter halos, meaning that their gravitational influence might have helped shape the distribution of galaxies. This idea isn't just theoretical. Observations of the large-scale structure of the universe show that galaxies aren't randomly scattered but instead form a vast cosmic web. Some models suggest that if cosmic strings existed, they could have played a role in creating these structures by acting as gravitational anchors that drew matter together. If that's the case, then cosmic strings wouldn't just be relics of the past. They would have actively shaped the universe we see today. And then there's the possibility that cosmic strings might not be entirely made of ordinary matter at all. Some researchers have proposed the idea of superconducting cosmic strings, strings that carry currents of exotic particles, possibly even dark matter itself. If such strings exist, they could generate powerful magnetic fields and produce bursts of high-energy radiation when they interact with other cosmic structures. This leads to another fascinating prediction: cosmic string loops. Unlike infinitely long cosmic strings that stretch across the universe, loops of cosmic strings could form when parts of a string reconnect with themselves. These loops wouldn't be static. They would vibrate and shrink over time, emitting bursts of gravitational waves as they lose energy. If such loops exist, they could be among the best candidates for detection. Some researchers believe that the mysterious fast radio bursts, FRBs, brief, intense pulses of radio waves from deep space, might be linked to cosmic string loops. If a loop were to collapse and release a massive burst of energy, it could produce an FRB-like signal. And if cosmic strings do produce gravitational waves, that means we might already have the tools to detect them. The Laser Interferometer Gravitational Wave Observatory, LIGO, and other gravitational wave detectors have been scanning the universe for ripples in spacetime caused by colliding black holes and neutron stars. But if an unusual, repeating pattern of gravitational waves is ever detected, one that doesn't match what we expect from black holes, it could be the signature of a cosmic string. But what about the more speculative possibilities? Could cosmic strings ever be used for something beyond just observation? Some physicists have entertained the idea that cosmic strings could be manipulated, perhaps even harnessed for energy. Theoretically, a cosmic string could contain more energy per centimeter than an entire planet. If an advanced civilization, perhaps even humans in the distant future, could find a way to tap into that energy, it could provide a near-infinite power source. And then there's the most mind-bending possibility of all, cosmic strings as shortcuts through space-time. Some models suggest that if two sections of a cosmic string were connected, they could form a stable wormhole. Unlike the theoretical wormholes proposed in general relativity, which require exotic matter to remain open, a cosmic string-based wormhole might already be naturally stable. If this is true, it could mean that cosmic strings are gateways across the universe, potentially allowing for faster-than-light travel. Imagine a civilization that discovered a cosmic string stretching across galaxies. If they could manipulate it, they might be able to use it as a highway through space, bypassing the limitations of conventional travel. Of course, this remains purely speculative. Right now, we don't even have direct evidence that cosmic strings exist. But the search is intensifying. As gravitational wave detectors become more sensitive, as radio telescopes scan the sky for unexplained signals, and as our understanding of fundamental physics deepens, we might finally get an answer. And if cosmic strings do turn out to be real, they won't just be a scientific curiosity. They will rewrite our understanding of the universe. They could be the missing link between particle physics and cosmology, the key to unlocking the secrets of the early universe, and possibly even a stepping stone to interstellar travel. So the next time you look up at the stars and wonder what's out there, remember that beyond the galaxies, beyond the black holes, beyond everything we can see, there might be something even stranger, thin, invisible threads stretching across the cosmos, holding the universe together in ways we have yet to comprehend. If cosmic strings exist, then they could be the ultimate bridges between different realms of physics, connecting quantum mechanics, general relativity, and even ideas about the multiverse. Their very nature challenges our current understanding of space-time, forcing us to consider possibilities that were once thought to be purely theoretical. One of the most fascinating consequences of cosmic strings is the way they distort space-time. Unlike traditional massive objects, which curve space around them due to their mass, cosmic strings create a different kind of distortion. They don't just bend space. They create a conical space-time structure. Imagine cutting a piece out of a two-dimensional surface and then stitching the remaining parts back together. This would create a sharp defect, similar to the way cosmic strings alter space-time. This unique distortion leads to one of the most bizarre effects of cosmic strings: gravitational lensing without mass. Normally, when light bends around an object, it's because of the object's gravitational pull. A black hole, for instance, bends light due to its intense gravity. But cosmic strings don't need mass to achieve this effect. Instead, their very presence alters the fabric of space-time itself, causing light to bend in unexpected ways. If a cosmic string were positioned between us and a distant galaxy, we might see double images of that galaxy, as light from it would take two different paths around the string. This effect, sometimes called double imaging, would be a telltale sign of cosmic strings. Astronomers have been scanning the skies for such anomalies, but so far, no definitive evidence has been found. However, the universe is vast, and detecting something as thin and elusive as a cosmic string would require extreme precision. Some scientists suggest that upcoming telescopes, such as the James Webb Space Telescope and future radio telescope arrays, could provide new opportunities to search for cosmic strings through their gravitational effects. But there's another way cosmic strings might reveal themselves: through the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe. Any disturbances in spacetime, including those caused by cosmic strings, could leave subtle imprints on this radiation. By analyzing the patterns in the CMB, scientists might be able to spot the signature of a cosmic string network stretching across the early universe. If detected, these imprints could provide a direct link to the conditions of the universe mere moments after the Big Bang. That's because cosmic strings, if they exist, would have formed during the earliest phase transitions of the universe, possibly in the first trillionth of a second. This means they could offer insights into high-energy physics far beyond anything we can recreate in laboratories. And here's where things get even wilder. Some theories suggest that cosmic strings might not just be relics of our own universe but could be bridges to other universes entirely. In certain models of string theory and the multiverse, cosmic strings might act as connectors between different regions of reality. If this is true, then cosmic strings could serve as natural pathways between parallel universes, creating a type of cosmic shortcut. Could this mean that somewhere, hidden within the vastness of space, there exists a cosmic string leading to an alternate universe? If so, would it be possible to interact with it, or even travel through it? Right now, these ideas remain speculative, but they hint at a reality far stranger than anything we currently comprehend. Meanwhile, there's also the question of how cosmic strings might interact with black holes. Since cosmic strings carry enormous amounts of energy, some scientists have theorized that if a cosmic string were to pass near a black hole, it could become trapped in its gravitational pull. This could lead to fascinating scenarios where black holes wrap cosmic strings around themselves, potentially altering their properties. One particularly extreme possibility is that a cosmic string could be stretched and accelerated by a black hole, causing it to whip around space at nearly the speed of light. This could create intense bursts of radiation or even exotic gravitational wave signals unlike anything we've seen before. Some researchers believe that detecting such signals could provide indirect evidence of cosmic strings. But beyond all these scientific implications, cosmic strings also raise profound philosophical questions. If they exist, what does that say about the nature of reality? Are they evidence of deeper physical laws we have yet to uncover? Do they point to a more fundamental structure of space-time that is hidden from us? And perhaps most intriguingly, if cosmic strings are remnants of the universe's earliest moments, could they carry information about what came before the Big Bang? Some speculative theories suggest that cosmic strings might have existed even in a prior cosmic cycle, surviving the collapse of a previous universe and re-emerging in our own. If true, then studying cosmic strings could be like looking at fossils from a past cosmos, offering clues about a time before time itself. This is why the search for cosmic strings is more than just an academic pursuit. It's a journey toward understanding the deepest mysteries of existence. Whether they are real or not, the mere possibility of cosmic strings forces us to rethink everything we know about the universe. They challenge our assumptions, push the boundaries of physics, and open up new frontiers of discovery. So, as astronomers continue scanning the heavens, searching for the faintest traces of these invisible cosmic threads, we are left with one undeniable truth: the universe is far more mysterious than we ever imagined. And whether or not we find cosmic strings, the questions they raise will continue to shape our quest to understand the cosmos. If cosmic strings exist, they could be one of the most significant discoveries in modern physics, offering a direct link to the universe's earliest moments. But if they do not exist, their absence could be just as revealing. It would force us to rethink the models of symmetry breaking and phase transitions in the early universe, potentially pointing us toward new physics that we have yet to uncover. One of the biggest challenges in detecting cosmic strings is that they are extraordinarily thin, so thin, in fact, that they make a human hair look massive by comparison. Yet despite their minuscule width, they would be incredibly dense and packed with enormous amounts of energy. A segment of cosmic string just a few kilometers long would have more mass than an entire planet. This extreme energy density means that, in theory, cosmic strings could create measurable effects on their surroundings, particularly through gravity and their interactions with matter and radiation. But here's where things get even stranger. Some theoretical models suggest that cosmic strings may not just be floating remnants of the early universe. Instead, they could still be actively forming and evolving today, albeit in ways that are incredibly difficult to observe. If the right conditions exist, cosmic strings could undergo reconnections, where two segments of string collide and merge or break apart. These reconnections would release bursts of energy, potentially producing gravitational waves, which are ripples in spacetime that can be detected by observatories like LIGO and Virgo. The detection of gravitational waves has already revolutionized our understanding of the universe, allowing us to observe cosmic events such as black hole mergers and neutron-star collisions. But if cosmic strings are real, they could produce a completely different type of gravitational wave signature, one that doesn't come from colliding objects but rather from the vibrations and oscillations of the strings themselves. These gravitational waves would be incredibly faint, but with advancements in detection technology, future experiments might be able to pick up their unique signals. Some researchers have even proposed that the gravitational wave background we've already detected could contain hidden evidence of cosmic strings. If this turns out to be true, it would be one of the most groundbreaking discoveries in physics, confirming that cosmic strings are not just theoretical constructs but real, physical entities shaping the cosmos. But cosmic strings don't just challenge our understanding of gravity, they also have profound implications for the fundamental forces of nature. In some variations of string theory and grand unified theories, cosmic strings are directly connected to extra dimensions of space. If these theories are correct, then cosmic strings might not just be one-dimensional defects in our universe but could be linked to higher-dimensional structures beyond our current perception. This leads to a truly mind-bending possibility. What if cosmic strings are not just remnants of the past but gateways to new physics? Could they be connected to hidden dimensions, parallel universes, or even new forms of matter and energy that we have yet to discover? Some physicists speculate that cosmic strings could interact with dark matter in unexpected ways, potentially serving as cosmic highways along which dark matter flows. If true, this could explain some of the lingering mysteries about the distribution of dark matter in the universe. And then there's the question of what happens when cosmic strings interact with themselves. If two strings collide, they might undergo loop formation, where a segment of string detaches and forms a closed loop. These loops would be incredibly dense and might survive for billions of years, radiating energy in the form of gravitational waves. In some cases, a loop of cosmic string could shrink down and vanish entirely, releasing all of its stored energy in a final burst. But in other cases, cosmic string loops might stabilize and continue to exist as long-lived structures drifting through space. Some researchers have even proposed that certain mysterious cosmic phenomena, such as unexplained gamma-ray bursts or ultra-high-energy cosmic rays, could be the result of decaying cosmic string loops. If that's true, then the universe could be teeming with the remnants of ancient cosmic strings, quietly influencing the cosmos in ways we have yet to recognize. This raises an even bigger question. Could cosmic strings have played a role in the formation of galaxies and cosmic structure? Some theories suggest that in the early universe, cosmic strings might have acted as seeds around which galaxies formed. Their immense energy and gravitational effects could have drawn in surrounding matter, helping to shape the large-scale structure of the cosmos. If so, then every galaxy we see today, including our own Milky Way, might owe its existence, at least in part, to the presence of cosmic strings billions of years ago. But if cosmic strings did influence galaxy formation, then there should be traces of their influence in the cosmic web, the vast, interconnected structure of galaxies and galaxy clusters that spans the universe. Some astronomers are searching for unusual alignments or patterns in this cosmic web that might hint at the past presence of cosmic strings. If they find such evidence, it could be a revolutionary breakthrough in our understanding of cosmic evolution. Yet despite all these possibilities, the search for cosmic strings remains one of the most difficult challenges in modern physics. Their thinness, their immense energy, and their potential ability to move at nearly the speed of light make them incredibly elusive. Even if one were drifting through our solar system right now, it might be nearly impossible to detect with our current technology. But that doesn't mean they aren't out there. The universe is filled with mysteries, and cosmic strings might be one of the biggest. If they exist, they could rewrite our understanding of space-time, fundamental forces, and the very nature of reality itself. And if they don't exist, their absence could force us to rethink some of our most deeply held assumptions about the early universe. Either way, the search continues. Scientists will keep scanning the skies, analyzing gravitational wave data, and searching for the subtle distortions in spacetime that cosmic strings might leave behind. And as technology advances, our ability to detect these hidden cosmic structures will only improve. So perhaps, one day, we will finally find the evidence we need. Perhaps a distant galaxy will appear split in two, revealing the unmistakable gravitational lensing of a cosmic string. Or perhaps a new gravitational wave signal will emerge, one that doesn't match anything we've seen before, hinting at the vibrations of a string stretching across the cosmos. Until then, cosmic strings remain one of the most tantalizing unsolved mysteries of the universe. They challenge our understanding of physics, hint at deeper realities beyond our perception, and force us to question what we truly know about the fabric of spacetime. And whether they exist or not, they remind us that the universe is far stranger, and far more fascinating, than we ever imagined. The implications of cosmic strings extend far beyond just their existence. If they are real, they could offer direct insight into the fundamental structure of the universe, linking seemingly disconnected areas of physics into a unified framework. The fact that they arise naturally in theories of high-energy physics suggests that their presence, or absence, could serve as a crucial test of these ideas. One of the most fascinating aspects of cosmic strings is their potential connection to string theory, one of the leading candidates for a theory of everything. String theory suggests that all fundamental particles are actually tiny vibrating strings, and some variations propose that cosmic strings could be macroscopic counterparts of these quantum strings. If this is true, then finding a cosmic string would not only confirm aspects of early universe physics but also provide real-world evidence for string theory itself, a discovery that would be nothing short of revolutionary. Some versions of string theory even suggest the existence of superstrings, which are essentially cosmic strings but with additional properties related to supersymmetry. These superstrings could interact with particles in exotic ways, potentially revealing new forces or even new dimensions of spacetime. If such strings exist, they could hold the key to answering some of the biggest open questions in physics, including the nature of dark matter and dark energy. Another fascinating possibility is that cosmic strings could serve as natural particle accelerators. Because of their immense energy and the way they interact with spacetime, they could create extreme conditions where particles are accelerated to near light speeds. This means that cosmic strings, if they exist, might be responsible for some of the highest energy cosmic rays ever detected. Scientists have long been puzzled by these cosmic rays, which appear to originate from nowhere, traveling at energies beyond what even the most powerful human-made particle accelerators can achieve. If cosmic strings are the source, then studying them could help us understand the behavior of matter under extreme conditions, potentially even revealing new physics beyond the standard model. And if cosmic strings are connected to the fabric of spacetime itself, could they also play a role in time travel or warp drives? Some speculative theories suggest that if a cosmic string were to form a loop or interact with another string in just the right way, it could create distortions in spacetime that resemble a closed time-like curve. In other words, a pathway that could theoretically allow for time travel. While this remains highly speculative, it raises intriguing questions about the nature of causality, and whether spacetime itself has hidden properties we have yet to uncover. There's also the question of whether cosmic strings could be responsible for some of the unexplained anomalies in astrophysics. For example, certain gravitational lensing events, where light from distant galaxies is bent in unexpected ways, don't always match the predictions of conventional physics. Some researchers have proposed that these strange distortions might be caused by invisible cosmic strings, warping spacetime as they move through the universe. If this turns out to be true, then these hidden structures could be subtly shaping the cosmos without us even realizing it. And what about the possibility that cosmic strings could be hiding in plain sight? Some researchers have suggested that, rather than being singular, isolated defects, cosmic strings might exist in vast networks stretching across the universe. If such a network exists, it could be influencing the distribution of galaxies, the formation of large-scale cosmic structures, and even the behavior of dark matter. If these strings crisscross the universe, they might occasionally intersect with our solar system. Theoretically, if a cosmic string were to pass through the Earth, it would create a sudden, sharp gravitational disturbance, potentially causing tiny, but measurable, shifts in the positions of satellites and planetary orbits. So far, no such disturbances have been detected, but the possibility remains open. One of the biggest reasons cosmic strings remain so elusive is that their effects are incredibly subtle. Even though they are predicted to be enormously dense and energetic, their narrowness and rapid motion make them extremely difficult to observe directly. However, scientists are coming up with new methods to detect their presence, from searching for unusual gravitational wave signals to mapping unexplained distortions in the cosmic microwave background. And the search is only just beginning. As our technology improves, we may develop new ways to detect these elusive structures. Future space-based observatories, capable of detecting even the faintest ripples in space-time, could provide the key to unlocking the mystery of cosmic strings once and for all. If we do find them, it will change everything. It will confirm that the universe underwent a phase transition in its earliest moments, leaving behind scars in space-time that still exist today. It will give us a new window into the fundamental forces of nature, possibly revealing connections between gravity, quantum mechanics, and string theory. And it could open the door to discoveries we can't even imagine, new physics, new dimensions, or even entirely new aspects of reality. But until that day comes, cosmic strings remain one of the most tantalizing mysteries of the universe. They might be out there, stretching across the cosmos, invisible to our current instruments, but subtly shaping the universe in ways we have yet to understand. Or they might not exist at all, in which case their absence would be just as fascinating, forcing us to rethink our understanding of the early universe. Either way, the search for cosmic strings continues. Scientists are scanning the skies, refining their models, and pushing the boundaries of physics to uncover the truth. And as we venture further into the depths of space and time, we may finally unravel one of the greatest cosmic mysteries ever imagined. If cosmic strings are real, they could be the missing piece in our understanding of the universe's structure, evolution, and fundamental laws. Their existence would prove that the cosmos is not just a smooth expanse of spacetime but a dynamic, interconnected web of energy and tension. They would provide direct evidence that the early universe went through violent, phase-shifting transformations, leaving behind these scars in spacetime, scars that could still be influencing reality on a cosmic scale today. One of the most intriguing aspects of cosmic strings is their ability to store and release energy. Because they are essentially cracks in the very fabric of spacetime, they hold enormous tension, often described as being like a stretched rubber band under extreme pressure. When a cosmic string vibrates or interacts with another string, it can release some of this energy in the form of gravitational waves. These waves, rippling through spacetime, could serve as a cosmic signature, allowing us to detect strings indirectly, even if we can't see them directly. The discovery of gravitational waves in 2015 by LIGO was a historic moment in physics, proving that spacetime can ripple like a vast cosmic ocean. But what if some of these ripples are caused not just by colliding black holes and neutron stars, but by cosmic strings? If scientists detect an unusual, repeating pattern in gravitational waves, something that doesn't match the known signals of black holes or neutron stars, it could be a sign that a cosmic string has been disturbed somewhere in the universe. But there's another way cosmic strings might reveal themselves, through their impact on the cosmic microwave background, CMB. The CMB is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. It's one of the most well-studied phenomena in cosmology, but it still holds mysteries. Some researchers believe that cosmic strings, if they exist, should have left subtle temperature fluctuations in the CMB, tiny imprints that could serve as a cosmic fingerprint of their presence. This means that by analyzing the CMB with greater precision, we might be able to trace the scars of cosmic strings back to the dawn of time itself. If we find these imprints, it will confirm that the early universe went through a dramatic transformation, where cosmic strings were formed and then stretched out across the universe as space expanded. And what if cosmic strings are not just leftovers from the Big Bang, but active players in shaping the universe today? Some scientists propose that cosmic strings could act as seeds for galaxy formation. In the chaotic early universe, before stars and galaxies had formed, matter was distributed in a nearly uniform way. But something had to cause small clumps of matter to start coming together. Something had to break the symmetry and trigger the birth of structure. Some theories suggest that cosmic strings, if they were present, could have provided the gravitational pull needed to gather matter into denser regions, eventually leading to the formation of galaxies. If this idea is correct, then our very existence might owe itself, in part, to these unseen threads of energy stretching across the cosmos. Another profound question arises: are cosmic strings still forming today? Most theories suggest that they were created during the first fractions of a second after the Big Bang, but some versions of physics allow for the possibility that new cosmic strings could still be emerging. If the universe undergoes new phase transitions, perhaps related to dark energy, extra dimensions, or changes in fundamental forces, then new cosmic strings might be forming right now, somewhere in deep space. If that's true, then detecting a new cosmic string could give us real-time insight into how the laws of physics evolve. It would mean that the universe is not static, but still undergoing fundamental changes, with new structures emerging on cosmic scales. There's also the question of what happens if a cosmic string collides with a black hole. Since cosmic strings are regions of extreme energy and tension, their interaction with black holes could produce some of the most violent and energetic events in the universe. Some models suggest that if a cosmic string were to fall into a black hole, it could produce bursts of high-energy radiation, potentially detectable with future space telescopes. Even more intriguingly, some theorists have speculated that if two cosmic strings were to collide and reconnect, they might produce exotic forms of matter or even create temporary wormholes, shortcuts through space-time. This idea is purely theoretical, but it opens up the possibility that cosmic strings could be linked to some of the strangest and most mysterious aspects of physics, including the nature of space-time itself. And speaking of mysteries, could cosmic strings help explain the enigmatic nature of dark matter? Dark matter makes up about 85% of the universe's total matter, yet we still have no direct proof of what it actually is. Some theories propose that dark matter could be composed of exotic particles that formed alongside cosmic strings in the early universe. If these particles interact weakly with normal matter but strongly with cosmic strings, then studying strings could provide a direct window into the hidden world of dark matter. All of this raises a fundamental question: if cosmic strings exist, why haven't we found definitive proof yet? Part of the answer lies in the fact that cosmic strings are extremely thin and nearly invisible under normal conditions. Unlike black holes, which can be detected by their intense gravitational pull, cosmic strings don't have an event horizon or emit light. Instead, their effects are primarily gravitational, meaning we have to look for subtle distortions in spacetime rather than direct visual evidence. But as our technology advances, we are getting closer to finding these elusive structures. Future space missions, such as the Laser Interferometer Space Antenna, LISA, will be able to detect gravitational waves with far greater sensitivity than current detectors. If cosmic strings are out there, LISA or similar projects could pick up their signals, finally providing the evidence needed to confirm their existence. If we do detect cosmic strings, it will fundamentally reshape our understanding of the universe. It will show us that the fabric of reality itself is not smooth, but scarred, carrying the imprints of ancient cosmic events. It will connect some of the biggest mysteries in physics, quantum mechanics, gravity, and high-energy particle physics, into a single, unified picture. And just as importantly, it will remind us that the universe is still full of hidden wonders, waiting to be discovered. Whether cosmic strings turn out to be relics of the past or active forces shaping the cosmos today, they are a reminder that we have only scratched the surface of understanding our reality. The search for cosmic strings is more than just a scientific pursuit, it's a journey into the unknown, a quest to uncover the deepest secrets of existence. And as we continue to push the boundaries of physics, one thing is certain: the answers are out there, waiting to be found. If cosmic strings are real, then we are looking at a universe that is far stranger and more dynamic than we ever imagined. The discovery of these structures would prove that spacetime is not just a passive stage where celestial bodies move, but an active, evolving medium that carries the scars of its past. These cosmic scars, though invisible to the naked eye, may be governing the very shape of the universe, influencing the motion of galaxies, the distribution of dark matter, and even the laws of physics themselves. But there's another pressing question: what happens if a cosmic string breaks? Unlike a normal string, which would snap and release its energy in an explosion, cosmic strings are theorized to either loop in on themselves or reconnect in an event known as intercommutation. This process can cause small loops of cosmic string to detach, creating what some theorists call cosmic string loops. These loops don't just float passively through space. They are believed to shrink over time, radiating gravitational waves as they do so. If these loops exist, they would provide yet another way to detect cosmic strings. By looking for specific patterns in the gravitational wave background, scientists could determine whether these loops are out there, emitting energy as they oscillate and decay. Some researchers even suggest that if a cosmic string loop were to form near a black hole, it could create a burst of high-energy radiation, detectable by space telescopes. Now, imagine the implications if we were to find such a signal. It wouldn't just confirm that cosmic strings exist, it would tell us that the universe is still actively shaping itself, with remnants of its earliest moments still influencing cosmic events today. And if cosmic strings are still breaking and reconnecting, it raises the possibility that new ones could still be forming, hinting at unknown physical processes that we have yet to discover. This brings us to one of the most intriguing possibilities. Could cosmic strings be connected to extra dimensions? Some versions of string theory, the leading candidate for unifying gravity with quantum mechanics, suggest that cosmic strings might actually be projections of higher dimensional structures onto our three-dimensional universe. In this view, what we perceive as a long, thin thread of energy stretching across space could actually be a cross-section of something much larger, existing in extra dimensions beyond our perception. If this idea is correct, then studying cosmic strings could provide direct evidence for extra dimensions, something physicists have been searching for decades. It would mean that cosmic strings are not just scars in spacetime, but bridges to higher dimensional realms, potentially offering insight into the true nature of reality. And that leads us to the most mind-bending possibility of all. Could cosmic strings be linked to the multiverse? Some theories propose that if two cosmic strings were to collide, they could create a localized region of spacetime that is completely separate from our own, a kind of baby universe branching off from our reality. If this is true, then cosmic strings might not just be remnants of the past. They could be gateways to new universes, forming and evolving in ways we can barely comprehend. This is where the search for cosmic strings goes from theoretical to profoundly existential. If cosmic strings are out there, influencing the fabric of spacetime in ways we have yet to fully grasp, then they might hold the key to understanding where our universe came from, why it behaves the way it does, and whether other universes exist beyond our own. And if we do find them, if we detect their gravitational waves, observe their imprints on the cosmic microwave background, or even witness their interactions in real time, then we will have opened a new chapter in our understanding of the cosmos. It will mean that the universe is far more complex, interconnected, and mysterious than we ever imagined. The search for cosmic strings is more than just a quest for a new scientific discovery. It is a search for the hidden architecture of reality itself, a journey to uncover the unseen forces that have shaped the cosmos from the beginning of time. And as we continue to push the limits of technology and exploration, one thing is certain: the universe still holds secrets that could rewrite everything we think we know. But if cosmic strings truly exist, what does that mean for the future of the universe? Are they merely remnants of the past, or could they still be playing an active role in shaping cosmic evolution? Some researchers speculate that cosmic strings might still be influencing galaxy formation today, acting as invisible scaffolding that guides the motion of matter across vast cosmic distances. One of the most intriguing ideas is that cosmic strings might be responsible for the distribution of dark matter. Dark matter is one of the greatest mysteries in physics. It doesn't emit or absorb light, yet it exerts gravitational effects on galaxies. While many theories suggest that dark matter consists of exotic particles, some physicists have proposed that cosmic strings could be influencing the way dark matter clusters, providing an unseen framework that affects how galaxies move and form. If this is true, then detecting cosmic strings wouldn't just confirm a long-standing theoretical prediction, it could also help us solve the dark matter mystery. Observing how cosmic strings interact with galaxies and gravitational fields could give us clues about the composition of dark matter and whether it has a connection to these ancient structures. But let's take this idea even further. If cosmic strings are still shaping the large-scale structure of the universe, could they also affect the fate of the cosmos? One possibility is that cosmic strings could be tied to the ultimate fate of the universe. If they continue to stretch and evolve over billions of years, they might play a role in how the universe expands. Some models suggest that if cosmic strings remain present in large enough numbers, they could influence the acceleration of cosmic expansion, affecting how space-time evolves over time. In a scenario where cosmic strings are abundant, their energy could contribute to the eventual slowdown of expansion, potentially leading to a big crunch, where the universe contracts and collapses back in on itself. On the other hand, if cosmic strings are rare but still influential, they might contribute to the ever-expanding universe, pushing space-time outward indefinitely. There's even a more extreme idea. What if cosmic strings could be harnessed for energy or space travel? Since they contain enormous amounts of tension and energy, some theorists have proposed that, if humanity ever gains the ability to manipulate cosmic strings, they could be used as a source of power or even as a means of bending space-time. Imagine a civilization advanced enough to capture and control a cosmic string. If they could manipulate its tension and structure, they might be able to create artificial warps in space-time, effectively generating stable wormholes. These cosmic strings could then be used as a means of faster-than-light travel, providing a natural shortcut through the universe. This idea might sound like science fiction, but it's based on real physics. Some solutions to Einstein's equations suggest that cosmic strings could form loops that remain stable over time, and these loops could theoretically be used to generate gravitational distortions that allow for interstellar travel. But before we start dreaming of using cosmic strings as space highways, there's one major obstacle: we have to find them first. Despite decades of theoretical work, no direct observational evidence for cosmic strings has been confirmed. That doesn't mean they aren't out there. It just means that we haven't developed the technology to detect them yet. Scientists are actively searching for cosmic strings using a variety of methods. The most promising technique is gravitational wave detection. Instruments like LIGO and future observatories like LISA might be able to pick up the telltale ripples in space-time caused by cosmic string interactions. If a cosmic string were to snap or reconnect, it could produce a sudden burst of gravitational waves, providing definitive proof of their existence. Another method involves studying the cosmic microwave background. If cosmic strings existed in the early universe, they should have left subtle imprints on the radiation that permeates all of space. By analyzing this radiation with greater precision, scientists might be able to uncover evidence of these ancient structures, hidden within the faint glow of the early universe. There's also the possibility that cosmic strings could be detected through lensing effects. Because they are incredibly massive and dense, cosmic strings should have the ability to bend light as it passes near them. If we observe distant galaxies or quasars and notice unusual distortions in their light, it could be a sign that a cosmic string is passing between us and the distant object. With so many possible ways to detect them, the search for cosmic strings is one of the most exciting frontiers in modern physics. If we find them, we won't just be uncovering a new cosmic phenomenon. We will be unlocking a window into the fundamental nature of space-time itself. But what if we don't find them? What if cosmic strings never existed at all? That would mean that some of our most well-established theories about the early universe would have to be revised or even abandoned. It would suggest that the universe evolved in a way that we still don't fully understand, and it could point us toward new physics beyond our current models. Either way, the search for cosmic strings is a journey that will reshape our understanding of the cosmos. Whether they turn out to be real or a mathematical illusion, their study forces us to confront the deepest questions about the nature of reality. Are we living in a universe shaped by hidden structures? Do cosmic strings hold the key to understanding dark matter, gravity, or even extra dimensions? Could they be gateways to other universes, waiting to be discovered? As we continue to explore the cosmos, one thing remains certain: the universe still holds secrets far beyond our imagination, and the quest to uncover them has only just begun. The mysteries of cosmic strings have the potential to answer some of the most profound questions we have about the universe's origins, structure, and future. These hypothetical structures might not only be relics from the birth of the cosmos but also active players in its evolution, challenging everything we thought we knew about space-time, gravity, and matter itself. If cosmic strings do exist, they would serve as a direct window into the conditions of the early universe. Understanding them could allow scientists to test fundamental ideas about how space and time function on the grandest scales. One of the most astonishing implications is that the discovery of cosmic strings might reveal the true nature of the Big Bang itself. Since these structures are believed to have formed during the first moments after the universe's inception, they could offer crucial insights into the initial conditions of the universe, perhaps even offering a more complete picture of what happened during the first few milliseconds after the Big Bang. Could cosmic strings be remnants of the inflationary epoch, a brief but extraordinary expansion of space-time right after the universe began? Their existence could suggest that some of the most fundamental forces in the universe came into being during this time, influencing how our universe evolved. As scientists refine their search, using more sophisticated instruments to observe space, the detection of cosmic strings could signify a paradigm shift in our understanding of physics. The very discovery of these structures would indicate that the universe is not as uniform and predictable as we once thought. Instead, it could be filled with hidden, intricate features waiting to be uncovered. This would lead to a revolution in physics, altering our understanding of gravity, quantum mechanics, and cosmology. But let's not forget that while the hunt for cosmic strings might open up new avenues for understanding the universe, the implications of their existence would raise just as many new questions. For instance, could cosmic strings be involved in cosmological catastrophes? Since they carry such immense energy and tension, might they have the potential to influence cosmic events in ways that we cannot yet foresee? What might happen if cosmic strings were to collide with each other, or if they were influenced by the gravitational pull of black holes or other extreme cosmic events? Could they play a role in the end of the universe as well, perhaps contributing to some grand cosmic disaster? If cosmic strings are real, the discovery wouldn't just affect our understanding of cosmology. It would reshape the field of theoretical physics as a whole. Since they are so closely tied to concepts like quantum mechanics, string theory, and general relativity, cosmic strings would provide critical data for scientists working to unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Finding evidence for cosmic strings could be a crucial step toward understanding how these forces operate together, paving the way for a theory of everything, a single framework that could explain all physical phenomena. But what does this mean for humanity's future? If we were to discover cosmic strings and learn how to manipulate them, we could be looking at a whole new set of possibilities for space exploration and technology. The ability to study, and perhaps even utilize, cosmic strings could open up entirely new ways of thinking about how we might harness energy or travel across vast distances. The tension in these strings represents a tremendous amount of stored energy that could be tapped for future technologies, powering everything from intergalactic ships to new forms of renewable energy. But we must be careful not to get ahead of ourselves. Cosmic strings are still a theoretical concept. No definitive detection has been made. However, just the potential for such a discovery is enough to inspire awe and curiosity about the universe. Even if they remain elusive for now, the mere pursuit of understanding cosmic strings forces us to confront some of the most fundamental questions about the nature of space, time, and the cosmos itself. As our technology continues to improve and our observational capabilities expand, we may one day see these cosmic threads for ourselves. Until then, cosmic strings remain a tantalizing enigma, one of the many mysteries that fuels our quest to understand the universe at its deepest level. And no matter what the future holds, the exploration of cosmic strings reminds us of one unshakable truth: the universe is far stranger and more beautiful than we could ever have imagined. And so, as we continue to explore the vast and complex universe, we are constantly reminded that there is still so much we do not know. Cosmic strings might just be one of the many pieces of the cosmic puzzle that we have yet to fully uncover, and their discovery would not just be an academic milestone, but a profound moment in our understanding of existence itself. With each step forward in our search, we inch closer to answering some of the most fundamental questions about the nature of space and time, and perhaps, unlocking the very secrets of the universe. As scientists, physicists, and astronomers continue their quest to uncover the truth behind these fascinating structures, we can only imagine the incredible discoveries yet to come. Will cosmic strings eventually be found? Will they reveal the true nature of the universe, or will they remain an elusive part of the cosmic mystery? Only time, and further exploration, will tell. But for now, we are left with the thought-provoking question: what lies hidden within the very fabric of space-time, waiting for us to uncover it? As we continue our exploration of cosmic strings, we begin to realize that they might not just be a theoretical construct, but a cornerstone of the universe's very foundation. Their implications stretch far beyond mere scientific curiosity. They could help us answer questions that have baffled humanity for centuries. Questions about the origins of the universe, the nature of space-time, and the very forces that govern everything around us. One of the most fascinating aspects of cosmic strings is how they could help us bridge the gap between two of the most powerful frameworks in physics: general relativity and quantum mechanics. General relativity describes the gravitational force on a large scale, such as the interactions between stars, galaxies, and black holes. On the other hand, quantum mechanics governs the behavior of particles on the smallest scales, dictating how atoms and subatomic particles behave. These two theories have long been at odds when it comes to explaining the universe as a whole. While general relativity excels in large-scale applications, quantum mechanics takes the spotlight in the microscopic world. But when it comes to understanding the universe at its most fundamental level, especially when considering phenomena like cosmic strings, we are left with a sense that something is missing. Cosmic strings might provide the link between these two worlds. If they are indeed real, the way they warp space-time and their effects on gravity could offer insights into how quantum mechanics and relativity can coexist. Imagine for a moment that cosmic strings are the key to a quantum theory of gravity, a theory that unifies these two powerful frameworks and allows us to understand how gravity operates on the smallest scales. If this is the case, the discovery of cosmic strings would be nothing short of revolutionary, opening up an entirely new avenue of research in theoretical physics. It would force us to rethink everything we thought we knew about the universe, from the very structure of space-time to the fundamental nature of reality itself. Of course, there are still many challenges ahead in the search for cosmic strings. Despite their fascinating theoretical properties, we have not yet detected any definitive evidence of their existence. They are incredibly elusive, and their signatures are difficult to detect using current technology. However, this is not to say that we should give up the search. In fact, the search for cosmic strings is ongoing, with scientists using a variety of methods to try to find them. One of the most promising ways to detect cosmic strings involves studying the cosmic microwave background (CMB) radiation, an afterglow from the Big Bang that permeates the universe. This radiation contains subtle imprints of the conditions that existed in the early universe, and cosmic strings, with their immense energy, could leave a unique signature in this radiation. By studying the CMB in detail, we might be able to spot these imprints and confirm the existence of cosmic strings once and for all. Another method for detecting cosmic strings involves looking at the gravitational waves that ripple through space-time. These waves are produced by massive objects like black holes or neutron stars, but they could also be created by the movement and interactions of cosmic strings. If cosmic strings exist, they could generate gravitational waves with a distinctive pattern, one that we might be able to detect using future gravitational wave observatories. In recent years, the detection of gravitational waves has opened up a whole new way of observing the universe, and it is not out of the question that they could play a pivotal role in uncovering the mysteries of cosmic strings. While the search for cosmic strings is still in its early stages, the possibility of discovering them has already begun to change how we think about the universe. It has forced us to reconsider some of our most basic assumptions about the nature of reality, and it has sparked a renewed interest in the early universe and the forces that shaped it. The potential discovery of cosmic strings could also have far-reaching implications for the future of space exploration. If these structures are truly as powerful as they appear to be, they could provide us with new ways of understanding and manipulating the universe's most fundamental forces. Whether it's harnessing the immense energy of cosmic strings or using them as a stepping stone toward faster-than-light travel, the possibilities are truly mind-boggling. But as with any scientific breakthrough, we must approach the study of cosmic strings with caution and humility. The search for these structures is still in its infancy, and we are just beginning to scratch the surface of what they might reveal. However, the very possibility of their existence invites us to think bigger and more boldly than ever before. It challenges us to push the boundaries of what we know and explore the deepest mysteries of the universe. Ultimately, cosmic strings may remain elusive for years to come, or we may one day discover that they are a vital part of the cosmic tapestry, woven into the very fabric of space and time. Regardless of the outcome, the pursuit of knowledge about cosmic strings exemplifies the human spirit of curiosity and exploration. We may not have all the answers yet, but each step we take in the search for cosmic strings brings us one step closer to unraveling the profound mysteries of the universe. The story of cosmic strings is far from over. Whether or not they are discovered, their legacy will continue to shape the way we view the cosmos and our place within it. For now, we remain in awe of the vast, unexplored reaches of space, where mysteries like cosmic strings continue to fuel our imagination and drive our quest for knowledge. As we look up at the night sky, we are reminded that the universe is still full of unknowns, and it is in the pursuit of these unknowns that humanity finds its greatest sense of wonder. The potential discovery of cosmic strings is just one of many mysteries waiting to be uncovered, each promising to reveal more about the awe-inspiring nature of the cosmos and the forces that govern it. Whether we discover cosmic strings or not, the quest to understand the universe's deepest secrets will continue, shaping the future of science for generations to come. And in that pursuit, we will always be driven by one simple truth: the universe is far more mysterious, complex, and extraordinary than we could ever have imagined. As we continue to explore the nature of cosmic strings and their potential role in the universe, we realize just how deeply intertwined these theoretical objects could be with the fundamental forces that govern everything around us. If cosmic strings exist, their properties could open doors to understanding the very origins of the universe and how the laws of physics came to be in the first place. But even if we never detect them directly, the mere possibility of their existence challenges everything we think we know about the universe and encourages us to keep pushing the boundaries of our understanding. Consider for a moment the possibility that cosmic strings are linked to the earliest moments of the universe, moments right after the Big Bang when the universe was still in its infancy. During this period, the universe was undergoing rapid expansion and cooling, and the conditions were extreme. It's possible that, under such conditions, space-time itself became tangled in the form of cosmic strings. These strings would have formed due to phase transitions in the early universe, where certain fields or forces began to take on their present-day characteristics. In other words, the birth of cosmic strings could be closely tied to the evolution of the very laws of physics that govern the universe today. If cosmic strings were created in the early universe, they would be some of the oldest structures in the cosmos, carrying with them information about the conditions that prevailed just moments after the Big Bang. Studying cosmic strings could therefore provide a unique glimpse into the universe's early history, helping us better understand how the universe went from a hot, dense state to the vast, complex cosmos we observe today. The presence of cosmic strings could also help us unravel the mysteries of dark matter and dark energy, two of the most elusive and poorly understood components of the universe. Since cosmic strings interact with the fabric of space-time, they might have influenced the distribution and evolution of dark matter in the early universe, leaving behind clues that could help us unlock the secrets of these invisible substances. In the context of string theory, which proposes that the fundamental building blocks of the universe are not point-like particles but rather tiny, vibrating strings, cosmic strings take on an even more profound significance. String theory posits that these microscopic strings could be the fundamental units of matter and energy, vibrating in different ways to produce the particles and forces we observe. If cosmic strings exist, they might be a macroscopic manifestation of the very same principles described by string theory, offering evidence that this theory is more than just mathematical speculation. The discovery of cosmic strings could, in essence, provide a window into the quantum nature of reality, helping us to understand how the universe behaves on both large and small scales. But let's not get ahead of ourselves. The road to understanding cosmic strings is far from straightforward. Despite all the theoretical work that has been done, we still lack concrete evidence that these objects exist. This is where the role of modern technology becomes crucial. The detection of cosmic strings may rely on advanced instruments and observatories that are still in development, or in the early stages of operation. Take LIGO, Laser Interferometer Gravitational Wave Observatory, for instance, which has already revolutionized our understanding of gravitational waves by detecting ripples in space-time caused by merging black holes. In the future, similar technologies could be employed to detect the subtle effects of cosmic strings, possibly through gravitational waves generated by their movement or interactions. The next generation of telescopes and observatories, such as the James Webb Space Telescope and other ground-based detectors, will allow scientists to probe deeper into the cosmos than ever before. These instruments could help us detect the faint traces of cosmic strings in the cosmic microwave background radiation, or perhaps even provide a clearer understanding of how cosmic strings influence the behavior of light and other forms of radiation as they travel through space. This opens the door to new avenues of research, where we could examine the effects of cosmic strings on the surrounding environment and how they interact with other cosmic phenomena like black holes, neutron stars, and supernovae. What makes the search for cosmic strings so compelling is that it connects several seemingly disparate areas of physics. It combines elements of cosmology, general relativity, quantum mechanics, and string theory into a unified framework that could help explain some of the universe's most perplexing questions. How did space-time itself come into existence? What were the forces at play during the Big Bang? How do the laws of physics work on both the largest and smallest scales? Cosmic strings may hold the answers to all of these questions, and the potential discovery of these objects could be one of the most profound moments in the history of science. One of the most intriguing aspects of cosmic strings is their immense energy. These objects are theorized to have incredibly high mass per unit length, meaning they could store vast amounts of energy in a relatively small space. The energy of a cosmic string could be so intense that it would have a significant influence on its surroundings, warping space-time in a way that we might be able to detect through gravitational waves or other phenomena. In fact, the energy stored in a cosmic string could even be harnessed in the far future, though this is purely speculative at this point. If we were to ever master the technology required to manipulate cosmic strings, the potential applications could be staggering. We could theoretically tap into a new source of energy, or perhaps even use cosmic strings as a means of propulsion for interstellar travel. Yet, even if we do not learn to manipulate cosmic strings, their mere existence could revolutionize our understanding of the cosmos. In the same way that the discovery of gravitational waves or black holes has reshaped our view of space-time, the detection of cosmic strings could lead to new discoveries that alter our perception of reality itself. It would push the limits of human knowledge and show us just how much we still have to learn about the universe. At this point, we are still at the beginning stages of our quest to understand cosmic strings. While the theoretical framework has been laid out, we have only begun to scratch the surface when it comes to gathering empirical evidence. However, even this early exploration has opened up a world of possibilities. As technology advances, our ability to observe and measure the effects of cosmic strings will improve, allowing us to test these theories more rigorously. Cosmic strings represent one of the most exciting and mysterious phenomena in modern cosmology and theoretical physics. Whether they turn out to be a key piece of the cosmic puzzle or remain an intriguing possibility, their study has already expanded our understanding of the universe in profound ways. The search for cosmic strings is not just about finding a particular object in space, it's about unraveling the very fabric of reality itself. Every step we take in this quest brings us closer to understanding how the universe came to be, how it operates, and what mysteries still lie hidden beneath its vast expanse. As scientists continue to investigate the potential existence of cosmic strings, one thing is clear: the universe is full of mysteries waiting to be discovered. Cosmic strings may just be one of the many secrets that will change the course of human knowledge forever. The journey into understanding cosmic strings takes us into realms of theoretical physics and cosmology where the lines between imagination and scientific rigor blur. While these objects are still hypothetical, the excitement they generate among scientists is palpable. If cosmic strings exist, they could revolutionize our understanding of how the universe operates on the most fundamental level. These theorized structures are not just potential relics of the early universe. They could serve as the keys to unlocking some of the greatest mysteries about the nature of reality itself. One of the challenges scientists face when studying cosmic strings is the vastness of the cosmos itself. These strings are thought to stretch across vast distances, possibly even spanning galaxies. To detect them, we need to look at the universe in entirely new ways, utilizing tools and techniques that can explore the fabric of space-time itself. It's not just a matter of spotting a cosmic string as we would a distant star or planet. Instead, scientists must search for the subtle signatures that these strings might leave behind in the universe's more observable phenomena. For example, gravitational waves, ripples in the fabric of space-time, could provide one such signature. We know that cosmic strings, due to their massive energy and dense structure, could produce detectable gravitational waves when they interact with their surroundings. When cosmic strings move, collide, or stretch across the cosmos, the disturbances they cause in space-time could generate waves that we might be able to measure with the next generation of gravitational wave detectors. If we detect these waves, it would not only provide evidence of cosmic strings, but it could also offer us a new way of looking at the universe's past and understanding the dynamics of space-time itself. Moreover, the gravitational effects of cosmic strings could also manifest in lensing phenomena. Gravitational lensing occurs when the gravitational pull of a massive object bends the path of light as it travels toward us. This can cause distant objects to appear distorted, magnified, or even multiple in appearance. Cosmic strings, with their intense gravitational pull, could act as cosmic lenses, distorting light from distant galaxies or stars. Observing how light behaves around these strings could help us detect their presence. It might not be a direct image of the string itself, but the way it warps the light traveling through space could provide us with critical clues about their existence. Another avenue of exploration involves studying the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. The CMB is a faint radiation that permeates the entire universe and holds crucial information about its early stages. Any irregularities or anomalies in the CMB could hint at the presence of cosmic strings, as these objects could have left subtle imprints on the radiation as they formed during the universe's infancy. By closely examining the CMB, scientists could look for these imprints, using them as a sort of cosmic fingerprint that points back to the moment when cosmic strings might have come into existence. Despite these possibilities, there's no guarantee that cosmic strings will be found anytime soon. The search for these objects is ongoing, but the journey itself is as important as the destination. Even if we do not directly detect cosmic strings in the near future, the research being conducted on them continues to push the boundaries of our understanding of the universe. Each theoretical discovery, every new tool or technique developed to explore space, and each new observation made is a step closer to answering some of the most profound questions about the cosmos. One of the fascinating aspects of cosmic strings is their connection to the broader multiverse theory. The multiverse hypothesis suggests that our universe may not be the only one, but instead, a single bubble in a vast sea of other universes, each with its own set of physical laws. Some versions of the multiverse theory propose that cosmic strings could exist as connections or boundaries between these different universes. In this context, cosmic strings would not only be relics of the early universe but also potential bridges between different realities. This mind-boggling idea adds yet another layer of intrigue to the mystery of cosmic strings. This potential link to the multiverse also ties into the concept of vacuum domains. A vacuum domain is a region of space that exists in a different vacuum state, essentially, a region where the laws of physics as we know them are altered. Cosmic strings could be the remnants of such vacuum transitions, representing the boundaries where one set of physical laws gives way to another. If cosmic strings are indeed linked to these vacuum states, they could hold the key to understanding the very structure of the universe and how different realities or dimensions could be interconnected. At the intersection of these theories lies the possibility that cosmic strings are part of a grander, unified theory, a theory that could explain everything from the origin of the universe to the very nature of gravity, space, and time itself. The quest to understand cosmic strings is in many ways a search for a unified theory of physics. If we could understand these objects, it could be the final piece that helps us link quantum mechanics, which governs the very small, with general relativity, which governs the very large. This unification is one of the ultimate goals of physics, and cosmic strings could play a central role in that journey. While we're still far from fully understanding cosmic strings, one thing is certain: the potential implications of their existence are staggering. If these objects exist, they could change everything we know about the universe, from its origin to its ultimate fate. They could reveal the very nature of space-time, gravity, and even the fundamental forces that govern everything from galaxies to atoms. In many ways, cosmic strings represent the last frontier of cosmology, an unexplored region where science, philosophy, and imagination meet. Whether we find them or not, the pursuit of these objects will continue to inspire and challenge us to look deeper into the cosmos and understand our place in it. This journey may take decades, if not centuries, to fully unfold. But the search itself is an integral part of the human endeavor. It reminds us that, no matter how much we learn, the universe still holds vast mysteries, and there will always be more to discover. Cosmic strings, though still theoretical, are a shining beacon on the horizon of scientific discovery. They represent the unknown, and in their pursuit, we may uncover the secrets of the universe itself. Theoretical physics is often a game of pushing the limits of what we know and venturing into the realm of the unknown. They stretch our imagination, challenge our understanding of space-time, and force us to reconsider the very nature of reality. As our tools for exploring the universe become more advanced, and as we continue to refine our theories and models, the potential to find evidence of cosmic strings becomes more plausible. Perhaps one day, we'll look back on this period of cosmic exploration as a time when we were on the cusp of one of the greatest discoveries in the history of science. But until that day arrives, the mystery of cosmic strings remains one of the most intriguing puzzles in the universe, a riddle that calls to us from the farthest reaches of space. In our quest to understand them, we're not just searching for answers to a specific question, we're searching for the very framework that governs the universe itself. Whether they exist or not, cosmic strings will continue to inspire and provoke us to reach for the stars, ever curious about the universe and our place within it. The allure of cosmic strings continues to grow as our understanding of the universe deepens. These theoretical objects, which arise from the framework of modern physics, represent not just anomalies in space-time but the potential building blocks of a larger, more complex cosmic structure. While the hunt for their actual existence remains ongoing, the very idea of these objects forces us to reconsider how we think about the cosmos and the forces that shape it. Perhaps the most intriguing aspect of cosmic strings is the insight they could offer into the very birth of the universe. In the context of the Big Bang, the universe underwent rapid, dramatic transformations, including the inflationary period when space expanded exponentially in a fraction of a second. It was during these extreme conditions that certain topological defects, like cosmic strings, may have formed. These strings could have been frozen into space-time during this incredibly energetic period, remaining as cosmic remnants that are still there today. Understanding how cosmic strings might form during inflation could provide a window into the early moments of the universe, an era that remains largely beyond our reach. Inflation, as theorized, involves extremely rapid expansion, causing quantum fluctuations to become stretched over vast distances, creating the landscape of the universe as we know it. In this environment, topological defects like cosmic strings may have emerged from these fluctuations, woven into the very fabric of space-time. These objects, once created, could persist in the universe, offering us a glimpse of the conditions that dominated its infancy. However, while their potential formation is tied to the violent and chaotic processes of the early universe, cosmic strings also carry with them the possibility of offering us a unique kind of cosmic fingerprint. This could allow scientists to study the conditions at the very beginning of time, conditions that are incredibly difficult to simulate in laboratories or recreate through mathematical models alone. Cosmic strings could, in essence, serve as a bridge between the theoretical and the observable, offering a direct link to the beginning of the cosmos. As we look deeper into the cosmic horizon, the mystery of cosmic strings is intertwined with other fundamental questions that still challenge our understanding. For instance, if cosmic strings exist, how do they fit within the context of dark matter and dark energy, two of the most enigmatic components of the universe? Could these strings provide a potential link between these mysterious forces? Or could they be composed of new types of matter or energy that we have yet to discover? Dark matter and dark energy are thought to make up approximately 95% of the universe's total energy density, yet we know very little about their properties or origins. If cosmic strings could help us understand these elusive forces, it would be nothing short of revolutionary. The interaction between cosmic strings and dark matter might not be as far-fetched as it sounds. Some theoretical models suggest that cosmic strings could be made of a form of matter that interacts with dark matter, or they might act as a source of gravitational anomalies that we could use to detect dark matter. In a universe where much of the mass and energy remains hidden from our detection, cosmic strings could become a crucial tool in deciphering the true structure of the cosmos. Similarly, the connection between cosmic strings and the phenomenon of quantum gravity is one of the most exciting possibilities that these objects present. Quantum gravity is an area of theoretical physics that seeks to reconcile general relativity, which describes gravity on a large scale, with quantum mechanics, which governs the behavior of particles on a microscopic scale. In trying to understand how gravity operates at the quantum level, scientists have proposed a variety of theoretical constructs, including string theory, which aims to explain all fundamental forces in the universe as manifestations of tiny vibrating strings. Cosmic strings, if they exist, could offer a direct link to quantum gravity, bridging the gap between the quantum and relativistic worlds in a way that no other phenomenon can. The study of cosmic strings might help reveal the elusive quantum nature of spacetime itself, furthering our understanding of the most basic structures of the universe. Moreover, cosmic strings might also have a significant impact on astrophysical events. Their immense mass and energy could influence the dynamics of galaxies, stars, and even black holes. If these strings are indeed massive enough, their gravitational influence could potentially bend light around galaxies, distort the trajectories of stars, and even play a role in the formation or evolution of supermassive black holes. This would mean that the very growth and shape of galaxies could be influenced by the existence of cosmic strings, fundamentally altering how we think about galaxy formation and evolution. It's also worth considering the potential role of cosmic strings in the context of space-time singularities. Singularities, the points in space-time where gravity becomes infinite, are most famously associated with black holes. However, some models suggest that cosmic strings themselves could be the key to understanding the formation of singularities in the universe. Could these strings be the remnants of ancient cosmic catastrophes? Or perhaps they could be a source of new singularities, contributing to the mysterious phenomena that we observe at the centers of galaxies? The relationship between cosmic strings and singularities remains one of the most profound questions in theoretical physics, and exploring this connection could shed light on some of the most extreme environments in the universe. As we venture further into the investigation of cosmic strings, we find ourselves stepping into a frontier that has the potential to reshape everything we know about the cosmos. These objects, though still hypothetical, invite us to question the very foundations of space, time, and reality. While the tools to detect them are still being developed, the quest to understand cosmic strings is intrinsically tied to our desire to comprehend the most fundamental aspects of the universe. It's important to note that the study of cosmic strings is just one piece of a much larger puzzle. Theories of everything, grand unification theories, quantum field theory, and string theory all interweave to create a comprehensive understanding of the universe. Cosmic strings could play a central role in uniting these disparate ideas into a single framework that explains the forces of nature, the origins of the universe, and perhaps even the future evolution of spacetime itself. To fully appreciate the implications of cosmic strings, we must step back and recognize that these are not just obscure, abstract objects but rather potential clues to understanding the nature of the universe at the most fundamental level. Each step toward detecting them, whether through gravitational waves, cosmic background radiation, or gravitational lensing, is a step closer to unlocking the secrets of the cosmos. In this quest, humanity continues to push the boundaries of what we know, reaching ever further into the vastness of space, exploring the hidden dimensions of reality, and seeking to answer questions that have fascinated us for millennia. Cosmic strings represent a bold frontier in this journey, one that promises to challenge our understanding and expand the horizons of scientific inquiry. The possibility that these objects might hold the key to unlocking the deepest secrets of the universe is both humbling and exhilarating. As we continue to search for cosmic strings, whether they exist or not, we are reminded of the infinite mysteries that still lie ahead in the cosmos. And as we strive to uncover these mysteries, we are reminded of our place in the universe, not as passive observers, but as active participants in the ever-unfolding story of the cosmos. The search for cosmic strings is not just about finding a new phenomenon, it's about looking deeper into the very nature of the universe, unraveling the threads that bind it together, and understanding the fundamental laws that govern everything from the tiniest subatomic particles to the vast expanse of the galaxies. Cosmic strings, whether real or theoretical, embody the spirit of scientific exploration, pushing us to ask bigger questions, seek deeper answers, and never stop exploring the infinite possibilities of the universe. As we continue to explore the possibility of cosmic strings, the excitement surrounding them is undeniable. It's not just their theoretical implications that make them so captivating, it's the potential for new discoveries, revelations that could completely alter our understanding of the universe. But, of course, to truly understand the importance of cosmic strings, we need to step into the realm of the unknown and the unimaginable. We're talking about phenomena that transcend even the limits of our most advanced scientific knowledge. Imagine for a moment that we find evidence of cosmic strings. What would that mean for the universe as a whole? What implications would it have for everything from the birth of the cosmos to the forces that govern its expansion? The discovery of cosmic strings would be a momentous event, one that could potentially unlock entirely new branches of science. But before diving into the consequences of such a discovery, it's important to pause and appreciate the complexity of these potential objects. Cosmic strings are not simply long, thin threads of matter, they are far more intricate than that. The idea that they could be woven into the very fabric of space-time suggests that they represent something much deeper, a type of flaw or imperfection in the structure of the universe itself. This could mean that they are not just a remnant of the past, but also a gateway to understanding how the universe has evolved and will continue to evolve. The more we learn about cosmic strings, the more we realize how fundamental they could be to the overall structure of reality. The concept of space-time itself, which we often think of as a static background to the events that take place in the universe, could be far more malleable and dynamic than we ever imagined. Space-time may not be an unchanging stage upon which cosmic events unfold. It may, in fact, be a much more active participant in the drama of existence. If cosmic strings are indeed real, they may represent the evidence of this hidden dynamism. In fact, the existence of cosmic strings could help explain the anisotropies, irregularities, in the cosmic microwave background radiation, which is the faint glow left over from the Big Bang. This radiation contains subtle patterns that reveal the structure of the early universe. If cosmic strings existed during this time, they could have left imprints in the form of gravitational waves or other distortions in spacetime, providing a unique signature that could be detectable even today. Finding such imprints would not only confirm the existence of cosmic strings but also give us invaluable information about the processes that occurred during the universe's infancy. But there's more. In addition to revealing the origins of the universe, cosmic strings could also help us understand some of the more bizarre phenomena that we observe today. For instance, the question of why the universe appears to be flat on large scales, why distant galaxies are uniformly distributed across the cosmos, remains one of the great mysteries in cosmology. Some researchers suggest that cosmic strings could have played a role in shaping the large-scale structure of the universe, helping to smooth out irregularities and contributing to the uniformity we observe. This, in turn, could provide insight into the ongoing expansion of the universe. Additionally, cosmic strings could help us unlock the mysteries of gravitational waves, ripples in space-time caused by massive cosmic events, such as colliding black holes. These waves carry information about the most violent events in the universe, and detecting them has become a major focus of modern astronomy. The connection between cosmic strings and gravitational waves is still speculative, but some theories suggest that the collision of cosmic strings could generate waves that are detectable by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory. These waves could potentially reveal hidden aspects of the universe's evolution, providing a unique opportunity to study the dynamics of space-time itself. Theoretical work on cosmic strings is not just confined to understanding their role in the early universe. It also involves thinking about how these objects might behave over time. Could they evolve into new structures, or perhaps even interact with other fundamental forces in ways that we can't yet predict? Some scientists suggest that cosmic strings could eventually decay, slowly losing their energy, and eventually disappearing from the universe. This process, if it occurs, could have a profound impact on the long-term evolution of the universe. The way in which cosmic strings dissipate their energy and the consequences of that decay could provide clues to the ultimate fate of space-time. Furthermore, the implications of cosmic strings extend beyond our own universe. Some cosmologists speculate that the discovery of cosmic strings could provide evidence for the multiverse theory, the idea that our universe is just one of many in a larger cosmic structure. If cosmic strings are a product of the early universe, and if they could potentially exist in different forms in other universes, this could serve as evidence that our universe is part of a larger network of parallel universes. Such a discovery would completely alter our understanding of the cosmos, revealing that the universe we observe is just one part of a much broader and more complex reality. The concept of a multiverse, once relegated to the realm of science fiction, could become a legitimate scientific hypothesis if cosmic strings are confirmed. This could open up entirely new avenues of research, with far-reaching implications for everything from the nature of time to the very origins of existence. It would challenge our fundamental understanding of what it means for something to exist, and what it means for the laws of physics to govern that existence. Beyond these theoretical implications, the discovery of cosmic strings would also have profound effects on our practical understanding of the universe. The more we learn about how these objects behave and interact with the fabric of space-time, the more we can improve our ability to detect them. For instance, the discovery of cosmic strings might lead to new methods for detecting dark matter and dark energy, two of the most elusive and enigmatic components of the universe. The interaction between cosmic strings and these mysterious forces could reveal previously hidden aspects of the universe's structure, ultimately bringing us closer to understanding the true nature of space-time. In this sense, the pursuit of cosmic strings is not just an academic exercise. It's part of a larger effort to unravel the mysteries of the universe itself. Each new discovery, whether theoretical or observational, brings us one step closer to answering the fundamental questions that have perplexed humanity for centuries. What is the nature of space and time? How did the universe come to be? And what is our place in the grand cosmic scheme? Cosmic strings, if they exist, represent a key to answering these questions. They offer us the potential to look deeper into the universe's past and understand the fundamental forces that shape it. Whether we ultimately find these objects or not, the search for cosmic strings serves as a reminder of how much there is still to discover, and how much we have yet to learn about the cosmos. With every new breakthrough in science, the universe seems to open up new doors, each one revealing more questions than answers. But it is through this process of inquiry, exploration, and discovery that we continue to expand our understanding of the cosmos. Cosmic strings, as theoretical as they may seem, are one of the many fascinating puzzles in the vast cosmic jigsaw, waiting to be solved. As we push the boundaries of knowledge and technology, we may one day uncover the truth about cosmic strings, unveiling their secrets and unlocking the next great chapter in our quest to understand the universe. Until then, we remain on the edge of discovery, peering into the unknown and striving to comprehend the infinite mysteries that lie beyond our reach. The search for cosmic strings is just one part of that journey, an ongoing adventure that continues to shape the future of science and our understanding of the universe. The implications of discovering cosmic strings extend far beyond the realms of theoretical physics and cosmology. They would revolutionize how we understand the very fabric of reality. With such profound implications for the foundations of space-time, the impact of cosmic strings would likely change not only our understanding of the universe but also our approach to science itself. Let's delve deeper into how this could affect the course of future discoveries. Imagine, for a moment, that a scientific breakthrough provides definitive proof that cosmic strings exist. This would be an earth-shattering moment in the world of science. For decades, cosmic strings were purely hypothetical, existing only in mathematical models and theoretical scenarios. But if we could finally detect them, it would be like discovering a missing piece of a puzzle that completes our understanding of the universe's birth and structure. One of the first questions that would arise from such a discovery is, how can we detect cosmic strings? For years, astronomers and physicists have speculated about how to find evidence of these theoretical objects. While the nature of cosmic strings makes them incredibly elusive, there are certain indicators that could point to their existence. As we touched on earlier, one of the primary methods for detecting cosmic strings would be through their effects on gravitational waves. The distortions in space-time caused by the interaction of cosmic strings could leave detectable imprints, which, if observed, would provide solid evidence for their existence. Gravitational wave detectors like LIGO and Virgo are on the cutting edge of this kind of research. These instruments are incredibly sensitive and designed to pick up the faintest ripples in space-time, generated by the most extreme cosmic events, like black hole mergers or neutron-star collisions. The next logical step in this line of research would be to look for gravitational waves produced by cosmic strings. What's fascinating about gravitational waves from cosmic strings is that they would likely exhibit a distinct pattern, unlike those from other known sources. These waves could provide us with valuable information not only about the strings themselves but also about the fundamental nature of spacetime. If we were to detect such a pattern, it would not just confirm the existence of cosmic strings but also give us the ability to study them in unprecedented detail. Now, let's take a step back and consider the broader implications of cosmic strings on our understanding of the universe's origins. As we know, the Big Bang Theory provides us with a model for the birth of the universe. According to this model, the universe began as an infinitely dense point and expanded rapidly in a process called cosmic inflation. During this time, the universe was incredibly hot and dense, and it's thought that various fundamental forces separated from one another, forming the foundation for the physical laws we observe today. However, the idea of cosmic strings adds a layer of complexity to this process. If cosmic strings were created during or after inflation, they could have played a crucial role in shaping the universe's early structure. Their existence would offer a new perspective on how the universe evolved and how cosmic forces interacted with one another. Some cosmologists theorize that cosmic strings could have contributed to the formation of galaxies, clusters, and even the large-scale structures that we observe in the universe today. Additionally, cosmic strings could provide new insights into the dark matter and dark energy that constitute most of the universe's mass and energy. These mysterious substances are still largely uncharted territory in physics, but some scientists speculate that cosmic strings may be connected to these enigmatic forces. Dark matter, which doesn't interact with light or electromagnetic radiation, is detectable only through its gravitational effects on visible matter. If cosmic strings are a part of this hidden sector of the universe, they could help us unlock the mysteries of dark matter and even dark energy, which remains one of the greatest challenges in modern physics. The presence of cosmic strings could also provide insights into the nature of gravity itself. As objects that warp spacetime, they may be able to teach us more about how gravitational forces work on the largest scales. Currently, we rely on Einstein's general theory of relativity to describe gravity, But this theory doesn't account for quantum mechanics, the theory that governs the very small scale of subatomic particles. Some researchers believe that the study of cosmic strings could offer a bridge between these two realms, ultimately leading to a unified theory of physics, one that could explain both the behavior of galaxies and the interactions between fundamental particles. Cosmic strings may also have a deeper relationship with the concept of time. In our current understanding, time is a linear progression, a dimension that moves forward from the Big Bang. But if cosmic strings are woven into the fabric of space-time, they could provide evidence that time itself may not be as straightforward as we think. Just as space-time can be warped by the presence of mass and energy, it's possible that cosmic strings could introduce new phenomena that challenge our conventional understanding of time. Could time be altered by the presence of cosmic strings, allowing for anomalies that we've yet to observe? It's an open question, one that continues to fuel speculation among theoretical physicists. The possibility of cosmic strings also raises questions about the future of the universe. As we explore the long-term evolution of cosmic strings, we have to consider their eventual fate. These objects, though extraordinarily thin, are immensely powerful. Could they eventually collapse, decay, or merge with other structures in the universe, resulting in cataclysmic events? Perhaps the ultimate death of a cosmic string could offer us clues about the future of space-time itself, potentially offering a glimpse into the end of the universe. The study of these phenomena could allow us to predict the universe's eventual fate, whether it's a gradual cooling and expansion or a dramatic and sudden end to everything. In this way, cosmic strings represent both the past and the future of the universe, a link between its fiery birth and its eventual demise. They are objects that transcend the typical boundaries of time and space, existing as markers of the universe's most profound transitions. Just as they could hold the key to understanding the forces that shaped the cosmos in its infancy, they may also be critical in understanding how the universe will end, whether through the collapse of space-time, the dissolution of matter, or some other fate we can't yet imagine. Of course, all of this remains speculative, and we are still far from being able to prove the existence of cosmic strings. But that's part of the excitement. The journey of scientific discovery is one of constant progress, with each breakthrough offering us a clearer picture of the universe. Whether cosmic strings are ultimately real or remain a theoretical construct, the pursuit of knowledge about them will undoubtedly lead to greater understanding of the universe and its fundamental workings. As we continue to observe the cosmos, both through telescopes and advanced theoretical models, the search for cosmic strings will remain a crucial part of the quest for knowledge. New technologies, from gravitational wave detectors to space-based observatories, could one day make it possible to detect these elusive objects, and in doing so, reshape our understanding of the universe in ways we can't yet predict. In the grand scheme of things, cosmic strings represent the frontier of human curiosity, where the laws of physics, the nature of time, and the fate of the universe itself converge. They are a tantalizing mystery, a cosmic puzzle that, if solved, could open the door to a deeper understanding of everything we know and hold dear. Their potential to answer the most profound questions of existence is limitless, and the search for them continues to inspire scientists, philosophers, and dreamers alike to look up at the stars and wonder, what mysteries lie beyond our reach, waiting to be discovered? As we continue to probe the nature of cosmic strings, the scientific community's fascination with these elusive objects isn't just about confirming their existence. It's about exploring what their discovery could mean for the very foundations of physics. Could cosmic strings provide the key to unlocking new aspects of the universe? Or are they merely a product of our mathematical imagination, another failed theory destined to be abandoned as we gain a deeper understanding of the cosmos? Only time will tell, but what's certain is that the search for cosmic strings has sparked an insatiable curiosity that will keep driving us to question everything we think we know about the universe. One of the most compelling aspects of cosmic strings is the idea that they are not just theoretical objects, but potentially hold answers to some of the most profound mysteries of the universe. They might be the missing link that bridges quantum mechanics and general relativity, two pillars of modern physics that have yet to be reconciled. General relativity, which describes gravity on a large scale, is incompatible with quantum mechanics, which governs the behavior of subatomic particles. Cosmic strings, with their extreme density and ability to warp space-time, could offer clues about how to unite these two theories into a single, cohesive framework, a theory of everything. But this isn't just about abstract mathematics or theoretical physics. It has real-world implications. The discovery of cosmic strings could potentially lead to new technologies, perhaps even new ways of manipulating space-time. After all, if we could understand how these objects interact with the fabric of space-time, who knows what innovations might arise from that knowledge? Could we one day harness the properties of cosmic strings for practical purposes, such as space travel or energy generation? It may seem far-fetched now, but as history has shown, many of the greatest scientific discoveries were once considered impossible. Moreover, if we managed to detect cosmic strings, the ramifications would extend beyond physics and into the realm of philosophy. If these objects truly exist, it would force us to reconsider our place in the universe. The existence of cosmic strings implies a universe far stranger and more complex than we could have ever imagined. It would challenge our concept of space, time, and the very nature of reality itself. Could these topological defects provide insight into the underlying structure of the cosmos, a kind of cosmic blueprint that governs everything from the formation of galaxies to the behavior of subatomic particles? As we continue to explore the universe and push the boundaries of what's possible in science, cosmic strings remain a tantalizing mystery, a thread that, if pulled, could unravel some of the most profound secrets of the universe. But for now, they remain out of reach, hidden within the folds of space-time, waiting for the right moment when we are technologically and intellectually prepared to uncover their secrets. With the ongoing advancements in technology and the increasing sensitivity of our instruments, it's only a matter of time before we make significant strides in detecting cosmic strings, if they indeed exist. Whether it's through the observation of gravitational waves, the analysis of cosmic background radiation, or the development of new mathematical models, the search for these enigmatic objects will continue to shape the future of astrophysics. One of the intriguing possibilities that arises from the study of cosmic strings is their potential to help us understand the fundamental nature of reality itself. If we accept the possibility that cosmic strings could be real, then they represent a type of glue that holds the fabric of space-time together. This opens up fascinating questions about the nature of space, time, and gravity. Could cosmic strings offer new insights into the origin of the universe? Could they provide a key to understanding the first moments after the Big Bang, when the universe was in its infancy? As we continue to probe deeper into the unknown, cosmic strings will remain an essential piece of the puzzle. Whether they exist or not, the search for them will inevitably lead us to new discoveries that challenge our current understanding of the cosmos and push the boundaries of human knowledge. In a way, cosmic strings serve as a reminder of the vastness and mystery of the universe. They are a symbol of our ongoing quest to understand the universe, a journey that has only just begun. Every step forward, every discovery we make, brings us closer to unlocking the deepest secrets of the cosmos. As the future of space exploration continues to unfold, we may find ourselves faced with more questions than answers. But it's through these questions that we grow and evolve as a species. Each new mystery presents an opportunity for discovery. And in the case of cosmic strings, that discovery could change everything we know about the universe. It's a thrilling prospect, one that invites us to dream big, think deeply, and never stop asking the fundamental questions that define our existence. But the most intriguing possibility of all is that cosmic strings might not just be relics of the early universe. They might still be out there, waiting to be found, hidden in the cosmic fabric of space-time, stretching across the universe like invisible threads. What if, right now, as you read this, there are cosmic strings passing through us, unseen and undetected, their existence just beyond our grasp? What if the universe is far stranger, more complex, and more interconnected than we can possibly imagine? The mystery of cosmic strings is one of those great unanswered questions that continues to captivate the imagination of scientists and dreamers alike. Whether or not we ever find concrete evidence for their existence is uncertain, but the journey to uncover their secrets will undoubtedly lead to discoveries that challenge everything we think we know about the cosmos. Cosmic strings, if proven to exist, could also reshape our understanding of dark matter and dark energy, two of the most enigmatic phenomena in the universe. While the exact nature of dark matter remains elusive, we know it accounts for a significant portion of the universe's total mass. Its gravitational effects can be observed in the way galaxies rotate and how light is bent around galaxy clusters. Similarly, dark energy, responsible for the accelerated expansion of the universe, continues to baffle scientists. Cosmic strings, due to their extreme mass and unique properties, could potentially provide a new framework for understanding both of these mysterious forces. Imagine, for a moment, that cosmic strings are real. They could provide an entirely new way of thinking about how matter behaves on both large and small scales. Given their proposed properties, extreme density and the ability to warp spacetime, cosmic strings could be the missing pieces in understanding the nature of gravity, spacetime, and the universe as a whole. Their discovery would not only offer solutions to current astrophysical mysteries, but could open up an entirely new field of study within the realm of theoretical physics. One aspect of cosmic strings that has intrigued scientists is the idea that they could have formed during the early moments of the Big Bang, when the universe was undergoing rapid expansion and cooling. As space-time itself stretched and settled into the structure we see today, cosmic strings might have emerged as topological defects, flaws or imperfections in the fabric of space-time, much like bubbles in a liquid. These defects could have been frozen into place as the universe cooled, leaving behind remnants that may still be detectable today. The very nature of these topological defects is a subject of intense debate. Some scientists propose that cosmic strings are one-dimensional objects, existing as incredibly long, thin, and infinitely stretching lines in space. These lines would be incredibly dense, exerting immense gravitational forces and possibly affecting the paths of nearby matter and light. Others believe that cosmic strings could be more complex, perhaps possessing additional dimensions or interacting in ways that we have yet to fully comprehend. The discovery of cosmic strings would offer a powerful tool for studying the early universe. These objects, by their very nature, are relics of the time when the universe was still in its infancy. If we can find a way to observe them directly, through the distortion of light, gravitational waves, or other indirect methods, they could provide crucial clues about the conditions that existed during the birth of the universe. This would allow scientists to probe the very moments after the Big Bang in a way that was previously impossible, giving us a deeper understanding of the origins of the cosmos. But finding cosmic strings, of course, is no easy task. These objects, by their very nature, are incredibly difficult to detect. Because they are so thin and diffuse, their direct observation would require instruments with an unprecedented level of sensitivity. Even indirect detection, through the study of gravitational waves or cosmic microwave background radiation, presents significant challenges. However, with advancements in observational technology, such as the ongoing development of more sensitive telescopes and gravitational wave detectors, scientists are optimistic that they will eventually uncover evidence of these strange, elusive objects. One potential avenue for detecting cosmic strings is through their effects on the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB is a key source of information about the early universe, providing a snapshot of the universe as it was just 380,000 years after the Big Bang. Any disturbances or anomalies in the CMB could offer clues about the presence of cosmic strings. For example, cosmic strings might leave behind imprints in the form of small temperature fluctuations in the CMB, providing a kind of fingerprint that could be detected by future missions such as the Planck satellite. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, are another promising way to detect cosmic strings. These waves travel across the universe, carrying information about the events that caused them. Cosmic strings, due to their immense density and the way they interact with the surrounding space-time, could produce gravitational waves detectable by sensitive instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo. In fact, some scientists believe that the detection of gravitational waves might be the best way to confirm the existence of cosmic strings, as their unique signature could be detected as a sudden burst or oscillation in space-time. Another exciting possibility is that cosmic strings could help explain the mystery of cosmic inflation, the rapid expansion of the universe in the moments following the Big Bang. Inflation theory suggests that the universe underwent an exponential growth spurt, increasing in size by a factor of more than 10 to the power of 26 in less than a second. This sudden expansion would have stretched out any small imperfections or irregularities in spacetime, potentially leaving behind traces of these early topological defects. Cosmic strings might be one such trace, a remnant of the early inflationary period that could help us understand how the universe evolved from its hot, dense origins to the vast, complex cosmos we observe today. Cosmic strings also have the potential to deepen our understanding of the nature of spacetime itself. General relativity, Einstein's theory of gravity, describes how spacetime is curved and warped by the presence of mass and energy. But general relativity is only one piece of the puzzle. When we consider the quantum scale, things become far more mysterious. The quantum field theory suggests that spacetime is not smooth but is instead subject to fluctuations and irregularities on the smallest scales. If cosmic strings exist, they could provide a bridge between these two realms, quantum mechanics and general relativity, offering a glimpse into a unified theory that describes all of the forces of nature. This idea, known as quantum gravity, remains one of the most elusive goals in modern physics. The nature of cosmic strings, with their ability to distort spacetime on a grand scale, could hold the key to understanding how gravity operates at the quantum level. If we can understand how cosmic strings influence the curvature of spacetime, we might be able to derive a new understanding of how gravity behaves at both large and small scales, potentially unifying the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, comprehensive theory. Despite the many unknowns, the search for cosmic strings continues to be one of the most exciting frontiers in modern science. The possibilities they present are vast, ranging from providing answers to some of the most fundamental questions about the universe to inspiring new technologies and ways of thinking about space-time. Even if cosmic strings ultimately turn out to be a figment of our mathematical imagination, the pursuit of this idea will have undoubtedly contributed to our understanding of the cosmos. As we venture further into the unknown, one thing remains certain: the universe is far more complex, strange, and beautiful than we can even begin to comprehend. Whether through the discovery of cosmic strings, the detection of gravitational waves, or the continued exploration of dark matter and dark energy, each new discovery brings us closer to unraveling the mysteries that lie hidden in the fabric of space-time. The search for cosmic strings is just one piece of this grand puzzle, but it is a piece that may hold the key to unlocking a deeper understanding of the universe itself. The journey to understand cosmic strings may be long and filled with uncertainty, but it is a journey that will continue to push the boundaries of our knowledge and shape the future of astrophysics. The future is full of potential, and with each step forward, we move closer to uncovering the true nature of the universe and our place within it. As the search for cosmic strings progresses, scientists are also exploring the broader implications these objects could have on the fundamental structure of the universe. The discovery of such cosmic phenomena could eventually lead to breakthroughs in our understanding of the universe's past, present, and future. While we may still be far from confirming their existence, the theoretical models that predict the presence of cosmic strings provide a fascinating lens through which we can view the cosmos. Whether or not we find direct evidence of cosmic strings, their potential to illuminate the mysteries of the early universe, space-time, and quantum mechanics is invaluable. The excitement surrounding cosmic strings isn't just limited to theoretical physics. Their implications could reach far beyond the confines of academic science and into real-world technology. Space-time itself, influenced by these potential defects, could provide new insights into energy, propulsion, and even communication. If cosmic strings can warp space-time in ways we haven't yet fully understood, they could lead to new methods of manipulating gravity or harnessing exotic forms of energy. The concept of manipulating space-time itself could one day make science fiction scenarios, like faster-than-light travel or time manipulation, a reality. These might sound outlandish now, but the same kind of wild, seemingly impossible ideas have inspired real-world technological advances throughout history. Furthermore, the study of cosmic strings could bring about profound philosophical implications as well. As we venture deeper into the cosmos and unlock its secrets, we are not only discovering more about the physical universe but also about our place within it. The pursuit of knowledge about cosmic strings challenges our very perception of reality. It calls into question the nature of existence, the limits of human understanding, and the fundamental structure of the universe itself. If the cosmos is, in fact, riddled with topological defects like cosmic strings, it would suggest that the universe is far more intricate and mysterious than we ever imagined. In this way, the pursuit of cosmic string research becomes more than just an intellectual endeavor. It becomes a quest to understand the very fabric of our reality. While much of the research surrounding cosmic strings remains theoretical, it is important to remember that the history of science is filled with once hypothetical concepts that have turned out to be real. From the discovery of atoms to the detection of gravitational waves, what was once thought of as speculative has often become a cornerstone of modern physics. Similarly, the study of cosmic strings, no matter how speculative it may seem today, could one day be a key chapter in our understanding of the cosmos. It could reshape our understanding of the universe's formation, its evolution, and the fundamental forces that govern everything from the smallest particles to the largest cosmic structures. For now, scientists are turning to both theoretical models and practical experiments in the hopes of finding more concrete evidence of cosmic strings. Observatories such as LIGO and the upcoming James Webb Space Telescope, JWST, are providing new and increasingly sophisticated methods of observing distant parts of the universe. Gravitational wave detectors are already providing us with a new way to study space-time, and future breakthroughs in technology could allow us to detect subtle phenomena that we currently cannot perceive. The more we explore the universe, the more we find that there are realms of knowledge that remain just beyond our reach. Cosmic strings, if they exist, may very well be one of those elusive frontiers. In the coming years, collaborations between theorists and observational scientists will be crucial to advancing our understanding of cosmic strings. Theoretical models must be tested against observational data, and new technological tools must be developed to improve our sensitivity to the subtle distortions in spacetime that might reveal these cosmic phenomena. As our detection methods become more refined, we may finally reach a point where we can observe cosmic strings directly or at least identify their indirect effects on the universe. At the same time, our understanding of cosmic strings may also evolve as new discoveries are made. New mathematical models, advancements in quantum field theory, and more precise measurements could all lead to a deeper understanding of cosmic strings' properties. It is also possible that future discoveries could force scientists to reconsider or even abandon some of the theories we currently hold about cosmic strings. Science, after all, is a constantly evolving field, where new ideas can reshape our understanding of the world in unexpected ways. One thing is certain: the pursuit of understanding cosmic strings will continue to push the boundaries of our knowledge. It is a quest that intertwines the realms of mathematics, physics, and cosmology, and has the potential to lead to new breakthroughs that could reshape our understanding of the universe. From the nature of spacetime itself to the fundamental forces that govern the cosmos, cosmic strings offer a tantalizing glimpse into the mysteries that remain hidden in the fabric of reality. It's also important to consider that while we often view cosmic strings through the lens of grand theoretical physics, they also connect to a broader range of topics in science. For example, they intersect with the study of high-energy physics and string theory, which posits that the fundamental building blocks of nature are not point-like particles but rather tiny, vibrating strings. These areas of research are tied to questions about the nature of forces, particles, and the fundamental constants of the universe. If cosmic strings do exist, they could open the door to new discoveries in string theory, quantum mechanics, and other areas of physics, providing insights that have far-reaching consequences beyond the study of spacetime itself. As we delve deeper into the cosmos, the idea of cosmic strings challenges our imaginations and invites us to explore the unknown. They are yet another reminder of how much we still have to learn about the universe, and how much more there is to discover. Even if we never find concrete evidence of their existence, the journey of exploring such fascinating concepts and theories is itself a testament to the wonder of scientific inquiry. The exploration of cosmic strings is not merely an academic pursuit. It is a pursuit that represents humanity's insatiable desire to understand the universe in all its complexity. It calls upon us to think bigger, dream further, and question the very nature of reality itself. If cosmic strings exist, they could unlock a treasure trove of knowledge about the origins of the universe, the nature of space-time, and the fundamental forces that shape everything we see around us. So, as scientists continue to search for answers and technologies improve, it remains an exciting time in the field of cosmology and theoretical physics. Cosmic strings may one day take their place as one of the most important discoveries in modern science. Until then, the quest to understand these mysterious objects and their role in the cosmos will continue to captivate the minds of those who dare to look beyond the stars, exploring the fabric of spacetime in ways that challenge our understanding of the universe itself. The ongoing exploration of cosmic strings has already contributed immensely to how we think about the universe. The journey is not only a pursuit of scientific truth, but also an intellectual adventure that challenges the foundations of our knowledge. By attempting to understand these potential anomalies in spacetime, scientists are essentially working to decipher the universe's most hidden codes. From their early days as theoretical models to their continued importance in modern physics, cosmic strings have remained a captivating and elusive subject. Their potential to shape our understanding of everything from black holes to the fabric of spacetime itself offers insights that extend far beyond the initial scope of cosmic string research. While there remains no direct detection of cosmic strings, we are beginning to recognize the profound implications these theoretical objects have for space and time. The consequences of their existence would be far-reaching, not just in cosmology but in many areas of physics. In some ways, cosmic strings could represent the final piece of a cosmic puzzle, one that ties together the forces of the universe in a way that is only beginning to be understood. One of the most tantalizing aspects of cosmic strings is their potential to bridge the gap between quantum mechanics and general relativity. These two pillars of modern physics, which govern the behavior of the very small and the very large, have long been at odds in certain respects. Quantum mechanics explains the behavior of particles at subatomic scales, while general relativity describes the large-scale structure of the universe, including the effects of gravity. Yet, despite their respective successes, these theories do not easily coexist, especially when it comes to the behavior of extreme objects like black holes or the early universe. Cosmic strings, with their connection to both spacetime and quantum fields, may hold the key to resolving some of the most perplexing questions about the relationship between these two domains. If cosmic strings truly exist, their interaction with spacetime could provide a concrete example of how quantum mechanics and general relativity might be unified into a single theory. This quest for a theory of everything, which seeks to combine all known forces in the universe into a single framework, is one of the most ambitious goals in theoretical physics. Cosmic strings could provide the key to understanding this theory, allowing scientists to study how quantum fluctuations on a cosmic scale might influence the very fabric of spacetime. In fact, the possible discovery of cosmic strings could help us understand how the universe itself came into being. These objects may hold the secrets to the conditions of the very early universe, immediately after the Big Bang. The period of rapid inflation that occurred just moments after the Big Bang created a universe that was homogeneous and isotropic on large scales, but it may have also created these tiny but significant defects in spacetime. Understanding how these defects may have influenced the evolution of the universe could provide us with a deeper understanding of how everything, stars, galaxies, and even life, came to exist. Moreover, cosmic strings might provide a new method for studying the cosmic microwave background, CMB, radiation. The CMB is the faint afterglow of the Big Bang and contains valuable information about the early universe. Scientists have already used this radiation to learn about the universe's age, composition, and the forces at play during its infancy. If cosmic strings existed and interacted with the surrounding spacetime, they could potentially leave imprints in the CMB, providing a fresh and unique way to probe the early universe. This could lead to new discoveries about how the universe expanded and cooled, and how matter began to take shape. The search for cosmic strings also raises important questions about the nature of dark matter and dark energy, two of the biggest mysteries in cosmology today. While dark matter is thought to account for the majority of the universe's mass, and dark energy is believed to drive the accelerated expansion of the universe, their exact nature remains unknown. Could cosmic strings be linked to these mysterious phenomena? Some theories suggest that cosmic strings might be a form of dark matter, or that they could somehow interact with dark energy in ways we have yet to comprehend. These connections, if true, could dramatically reshape our understanding of the universe's fundamental composition and its large-scale structure. Another exciting possibility is that cosmic strings could offer a new way of thinking about the origins of black holes. These dense, gravitationally powerful objects have long been a subject of fascination for scientists. Their ability to warp space-time around them has made them key players in our understanding of gravity. However, we still have much to learn about the formation of black holes and their relationship to the surrounding space-time. If cosmic strings are indeed real, they might help explain some of the more perplexing aspects of black hole formation and behavior. For example, cosmic strings could serve as the seeds around which black holes grow, or they could influence the dynamics of the accretion disks that surround black holes. These possibilities would open new avenues of research and could offer answers to questions that have remained unresolved for decades. The search for cosmic strings could also have practical implications beyond our theoretical understanding of the universe. For example, if these objects truly exist and can interact with spacetime in extreme ways, they could offer new insights into gravity and energy manipulation. In the far future, this might even lead to practical technologies that manipulate spacetime, enabling breakthroughs in fields such as propulsion, energy generation, or even time travel. While these ideas may sound like science fiction, the study of theoretical physics has historically led to practical advancements that were once thought impossible. It is not inconceivable that the exploration of cosmic strings could lead to similarly transformative discoveries. As the search continues, it is likely that we will encounter many challenges along the way. The detection of cosmic strings, if they exist, will require the development of increasingly sophisticated technology, as well as innovative new ways of interpreting observational data. It may take years, even decades, before we have a clearer picture of whether these objects truly exist and how they shape the universe. But the pursuit itself is what drives scientific progress. Each discovery, whether big or small, brings us closer to unlocking the ultimate mysteries of the universe. While it may be tempting to think of the study of cosmic strings as an abstract and esoteric pursuit, it is important to recognize the deep connections it has to the world around us. Every breakthrough in our understanding of the universe has the potential to change the way we live, the way we think, and the way we interact with the cosmos. Whether or not we ever detect cosmic strings, the questions they raise are at the forefront of human inquiry, inviting us to explore the very nature of reality. The search for cosmic strings is not just about finding new facts or validating theoretical models. It is about exploring the deepest mysteries of existence, pushing the limits of human understanding, and challenging everything we think we know about the universe. As we look to the stars, we are reminded that the universe is far more mysterious and complex than we could ever have imagined. Cosmic strings may be one of the many keys that will eventually unlock the secrets of the cosmos. Until then, we continue to push forward, driven by the insatiable curiosity that has defined humanity's quest for knowledge throughout history. As we continue to explore the nature of cosmic strings, it's essential to recognize the profound philosophical implications these theoretical objects bring to the table. The existence of cosmic strings challenges the very structure of reality itself, pointing to a universe that is far more intricate and complex than it might initially appear. For centuries, the pursuit of understanding the cosmos has been a journey of revelation and discovery, leading to dramatic shifts in our perception of the universe, our place within it, and the fundamental laws that govern everything. If cosmic strings do indeed exist, they would provide a direct window into the origins of space and time. These topological defects in space-time could potentially reveal information about the state of the universe just after the Big Bang, information that would otherwise be lost to time. Studying them would allow us to peer back into an era where the very fabric of reality was being shaped, offering clues about how the universe evolved from a hot, dense singularity to the vast, complex cosmos we observe today. The role of cosmic strings in shaping the universe's early conditions cannot be overstated. The early universe was a place of extreme temperatures and rapid expansion, and the interactions between fundamental forces were drastically different from what we see today. In this tumultuous environment, the formation of cosmic strings could have been a natural consequence of the phase transitions that occurred as the universe cooled and underwent significant shifts in its fundamental properties. These strings would have influenced the distribution of matter and energy, potentially playing a key role in the formation of galaxies and large-scale cosmic structures. Despite their fascinating potential, cosmic strings remain largely theoretical. In the absence of direct observational evidence, scientists have turned to indirect methods to probe their existence. The cosmic microwave background (CMB), for example, is one of the most useful tools at our disposal for investigating the universe's early history. By studying the subtle fluctuations in the CMB, scientists can detect traces of the conditions that prevailed in the moments after the Big Bang. If cosmic strings were present, their influence on the fabric of space-time could leave imprints in the CMB, which might be detectable using advanced observational instruments. Moreover, scientists are investigating the possibility that cosmic strings could help explain some of the anomalies we observe in large-scale cosmic structures. For example, the observed distribution of galaxies and clusters of galaxies doesn't always match the predictions made by standard models of cosmology. Some researchers have speculated that cosmic strings, as topological defects, might account for some of these discrepancies. The gravitational effects of cosmic strings could potentially create a web of connections between distant parts of the universe, shaping the large-scale structure of the cosmos in ways we are just beginning to understand. One particularly intriguing feature of cosmic strings is their potential to generate gravitational waves. Gravitational waves, ripples in the fabric of space-time caused by accelerating masses, were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. These waves, which were predicted by Einstein's theory of general relativity, provide a unique way of studying extreme cosmic events, such as the collision of black holes. If cosmic strings exist and interact with space-time in the ways theorists suggest, they could generate gravitational waves that might be detectable by next-generation instruments. The detection of gravitational waves from cosmic strings could provide some of the most direct evidence yet for their existence. These waves would carry crucial information about the properties of the strings, including their tension, mass, and potential interactions with the surrounding universe. The study of gravitational waves from cosmic strings could, therefore, serve as a powerful tool for exploring some of the most fundamental aspects of physics, including the nature of space-time, the role of dark matter, and the interplay between quantum mechanics and general relativity. Furthermore, the study of cosmic strings has deepened our understanding of the early universe's behavior. The presence of such topological defects could provide insights into how different forces came to be unified in the early moments after the Big Bang. Theoretical physicists believe that at extremely high temperatures, all the fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were once part of a single unified force. As the universe cooled, these forces gradually separated, giving rise to the distinct forces we observe today. Cosmic strings might represent an echo of this early phase transition, offering us a glimpse into the conditions under which the universe's fundamental forces were once unified. The nature of cosmic strings also ties into some of the most advanced ideas in modern physics, such as string theory. String theory posits that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings of energy. These strings exist in a higher dimensional space, and their interactions give rise to the particles and forces we observe in our three-dimensional universe. Some variations of string theory suggest that cosmic strings could be a natural consequence of the theory's higher dimensional structure, potentially providing a direct link between string theory and observable phenomena in the universe. Despite the challenges of proving the existence of cosmic strings, the search for them continues to inspire physicists and cosmologists around the world. The potential to uncover new truths about the universe's birth, its structure, and its fundamental forces is a powerful motivator for researchers. As technology improves and observational techniques become more advanced, it's possible that we will one day detect cosmic strings directly, or at least uncover more indirect evidence of their existence. This would represent one of the greatest breakthroughs in cosmology and theoretical physics. In the meantime, the search for cosmic strings serves as a reminder of the boundless curiosity and imagination that drive scientific discovery. It highlights the importance of thinking beyond the known and daring to explore the unknown. Whether or not cosmic strings are ultimately found, the pursuit of understanding them will continue to shape the way we think about the universe, pushing the boundaries of human knowledge and inspiring future generations of scientists to seek out the deepest truths of existence. As we stand on the precipice of further exploration into the nature of space-time, black holes, dark matter, and quantum mechanics, the concept of cosmic strings remains an alluring enigma. These hypothetical objects offer a unique opportunity to unify our understanding of the universe, bridging the gap between the infinitesimal world of quantum particles and the grand scales of cosmic phenomena. They also present a chance to probe the most extreme conditions in the universe, from the earliest moments of creation to the most mysterious corners of space. In the grand scheme of things, cosmic strings are not just a puzzle to be solved. They represent a key to understanding the fundamental nature of reality itself. Their potential to reshape our understanding of physics, cosmology, and the universe's origins makes them one of the most fascinating subjects in modern science. Whether they are eventually detected or remain theoretical constructs, cosmic strings will continue to captivate the imagination of scientists and lay people alike for generations to come. As we continue to explore the implications of cosmic strings, it's worth noting that their significance extends beyond just answering questions about the universe's origins. These topological defects, if proven to exist, could hold the key to understanding some of the most fundamental questions in physics. How did space-time come into existence? What caused the rapid inflation of the early universe? Can we ever achieve a unified theory of everything? Cosmic strings may hold the answers to these questions, or at least provide valuable insights that help us move closer to understanding the universe's deepest mysteries. One of the most tantalizing aspects of cosmic strings is their potential to unlock secrets about the very nature of space-time. Space-time, as we understand it, is the fabric that underpins everything in the universe. It is what allows us to experience the passage of time and perceive the distances between objects in space. Yet, space-time itself is not a simple, static entity. It is dynamic, capable of bending and stretching under the influence of mass and energy. The presence of cosmic strings could provide a profound new understanding of how space-time behaves under extreme conditions. These objects may not only warp space-time in their vicinity but may also reveal how space-time itself is constructed, offering clues about the nature of gravity, quantum mechanics, and the fundamental forces of nature. The study of cosmic strings could also help answer some of the most pressing questions about the structure of the universe. For instance, why does the universe appear to be so uniform on large scales, with galaxies and galaxy clusters distributed in a seemingly orderly fashion? Cosmic strings might offer a clue. Their existence in the early universe could have contributed to the formation of galaxies and other cosmic structures by influencing the distribution of matter and energy. These strings could act as scaffolds around which matter clumps together, helping to form the large-scale structures that we observe today. Furthermore, cosmic strings may also shed light on the elusive concept of dark matter. Dark matter is believed to make up a significant portion of the universe's mass, yet it remains invisible to current observational techniques. While its presence is inferred through its gravitational effects on visible matter, scientists are still unsure what dark matter actually is. Some researchers have proposed that cosmic strings could play a role in the distribution of dark matter, acting as a form of cosmic glue that helps to hold dark matter together. If this hypothesis is correct, it could revolutionize our understanding of dark matter and its role in the cosmos. In addition to their potential connection to dark matter, cosmic strings may also be linked to dark energy, another mysterious phenomenon that seems to be driving the accelerated expansion of the universe. Dark energy is thought to make up around 70% of the universe's total energy content, but its properties remain largely unknown. Some theories suggest that cosmic strings could interact with dark energy, potentially playing a role in the acceleration of the universe's expansion. If cosmic strings and dark energy are indeed related, their study could provide important insights into the fate of the universe, and help to resolve one of the most profound mysteries in cosmology. The search for cosmic strings is not just limited to theoretical predictions or mathematical models. As we mentioned earlier, scientists are using a variety of observational techniques to detect possible traces of cosmic strings in the cosmos. One of the most promising methods is the study of gravitational waves. Gravitational waves, as we now know, are ripples in the fabric of spacetime caused by the acceleration of massive objects. These waves travel at the speed of light, carrying information about the events that generated them. By studying the signals from gravitational waves, scientists hope to detect the faint signatures of cosmic strings and gain a better understanding of their properties. To achieve this, scientists have already begun to refine their search for gravitational waves in the hopes of identifying signals that could be associated with cosmic strings. As mentioned earlier, cosmic strings could generate gravitational waves due to their immense mass and the way they warp spacetime around them. These waves would likely be detectable using advanced instruments such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, which have already made significant breakthroughs in detecting gravitational waves from black hole mergers and neutron-star collisions. If cosmic strings exist and generate detectable gravitational waves, they could provide the first direct evidence of these fascinating objects. Another potential method for detecting cosmic strings involves the study of the cosmic microwave background, CMB. The CMB is the faint radiation left over from the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. By studying the CMB, scientists can learn about the conditions that existed during the early stages of the universe's evolution. If cosmic strings were present during this time, they could have left subtle imprints on the CMB, such as distortions or unusual patterns in the data. By carefully analyzing the CMB and comparing it with predictions from various models of cosmic strings, researchers hope to uncover evidence that could confirm or rule out their existence. While the search for cosmic strings is still ongoing, the possibility of discovering them has already led to a number of exciting theoretical developments. For example, some scientists believe that the detection of cosmic strings could provide a way to test and refine our understanding of string theory. String theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in more than 3 dimensions, with extra dimensions possibly explaining the behavior of forces like gravity. If cosmic strings were found to exist, they could provide a direct link between the observable universe and the higher dimensional space of string theory, helping to bridge the gap between quantum mechanics and general relativity. The discovery of cosmic strings would also have profound implications for our understanding of the universe's history and future. If these objects did form in the early universe, they could provide crucial information about the processes that took place during the Big Bang and the subsequent evolution of the cosmos. Cosmic strings could also help explain some of the phenomena we observe in the universe today, such as the distribution of galaxies, the formation of black holes, and the nature of dark matter and dark energy. In essence, the discovery of cosmic strings could unlock some of the deepest secrets of the universe, providing a new framework for understanding the cosmos at its most fundamental level. Despite the excitement surrounding the search for cosmic strings, there are still many challenges to overcome. For one, detecting cosmic strings directly is an incredibly difficult task. Their influence on the universe is subtle, and the signals they produce, whether in the form of gravitational waves or CMB distortions, are faint and difficult to isolate from other sources. As a result, the search for cosmic strings will require the development of increasingly sophisticated instruments and techniques. However, as our technology continues to advance, and as we learn more about the universe's fundamental structure, the likelihood of discovering cosmic strings may increase. The quest to understand cosmic strings is more than just a scientific endeavor. It is a journey that pushes the boundaries of human knowledge and challenges our most basic assumptions about the nature of the universe. Whether or not cosmic strings exist, the pursuit of understanding them will undoubtedly lead to new discoveries, insights, and questions that will continue to captivate the imagination of scientists and the general public alike. The mysteries of space are far from being solved, and the hunt for cosmic strings is just one piece of the larger puzzle that we are all trying to unlock. As we delve deeper into the nature of cosmic strings, we come to realize just how far-reaching their implications could be for our understanding of the universe. From their potential to help explain the very fabric of space-time to their ability to offer insights into dark matter and dark energy, cosmic strings represent a fascinating frontier in the world of theoretical physics. But just as with many other mysteries of the universe, the search for answers is not without its obstacles. One of the most intriguing aspects of cosmic strings is the question of their stability. These objects, if they exist, are predicted to be incredibly long and thin, stretching across vast distances in space. However, they are also thought to be extremely fragile. Some theories suggest that cosmic strings could be susceptible to breaking apart or decaying over time, while others propose that they could persist indefinitely, continuing to shape the universe for billions of years. The exact fate of these structures remains unclear, and much of the uncertainty surrounding cosmic strings comes from our limited understanding of how they interact with other forms of matter and energy. Theoretically, cosmic strings are predicted to form when space-time undergoes a phase transition, similar to how defects form in other materials when they cool down. This process is known as spontaneous symmetry breaking, and it's believed to have occurred during the early stages of the Big Bang. When the universe was still in its infancy, it may have experienced rapid inflation, causing space-time itself to stretch and expand. During this expansion, regions of space-time could have become out of sync, forming defects like cosmic strings. These defects, while fascinating, could also have profound consequences for the structure of the universe. In particular, their gravitational effects could create distortions in the fabric of space-time, warping the trajectories of nearby objects and even bending light. This effect, known as gravitational lensing, is something scientists are already familiar with when observing massive objects like black holes or galaxy clusters. If cosmic strings exist, they could create additional lensing effects, offering us another tool for studying the universe on a grand scale. These distortions could potentially be detected through the observation of distant galaxies, enabling scientists to indirectly map the locations of cosmic strings and gain a better understanding of their behavior. Interestingly, some scientists have speculated that cosmic strings could even play a role in the formation of black holes. According to one hypothesis, when two cosmic strings interact with each other, they could create a knot in spacetime. These knots could be so dense that they would collapse under their own gravity, forming black holes in the process. This idea has spurred a new line of research focused on the potential relationship between cosmic strings and black holes, and it raises the possibility that cosmic strings could contribute to the creation of some of the most mysterious objects in the universe. Moreover, cosmic strings may have an important role in the understanding of the early universe itself. During the first few moments after the Big Bang, the universe was in a state of extreme density and temperature. The laws of physics, as we know them, may not have applied in the same way they do now. Instead, exotic phenomena such as cosmic strings could have been the key to understanding the fundamental forces that govern the universe's evolution. If we are to piece together a coherent story of the universe's early stages, cosmic strings may provide the missing link between the observable universe and the quantum realm where the forces of gravity, electromagnetism, and the weak and strong nuclear forces are thought to converge. Furthermore, cosmic strings could also have an impact on the study of the multiverse theory, which proposes that our universe may not be the only one in existence. According to this theory, there could be many parallel universes, each with its own set of physical laws. If cosmic strings were present in multiple universes, they could provide a way to connect them, allowing us to study the interactions between different universes in a way that would otherwise be impossible. This notion is still highly speculative, but it adds another layer of intrigue to the study of cosmic strings, highlighting the potential for these objects to not only reveal the secrets of our own universe but also offer insights into the nature of reality itself. The relationship between cosmic strings and the fabric of space-time has profound implications for our understanding of gravity. Currently, our understanding of gravity is based on Albert Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by massive objects. However, general relativity has some limitations, particularly when it comes to explaining phenomena at the quantum level. One of the major goals of modern physics is to find a theory that can unify general relativity with quantum mechanics, creating a theory of everything that explains all of the forces of nature within a single framework. Cosmic strings, as hypothetical objects that may exist at the quantum level, could offer a crucial link between these two domains of physics. By studying the behavior of cosmic strings, scientists may be able to gain new insights into the workings of spacetime on the smallest scales, potentially providing the key to unlocking a unified theory of physics. If cosmic strings exist, they could provide a new form of quantum gravity that incorporates both the principles of general relativity and the strange behavior of subatomic particles, allowing us to better understand the interactions between matter, energy, and the fundamental forces of nature. The search for cosmic strings, though still in its early stages, is already generating excitement among scientists and cosmologists. The possibility that these objects could exist, hidden in the vast expanse of space, undetectable to the naked eye, represents a tantalizing mystery that could revolutionize our understanding of the universe. Whether they are the remnants of the early universe or the building blocks of a hidden cosmic structure, cosmic strings hold the potential to answer some of the most profound questions in modern science. However, as with all scientific inquiries, there is still much we don't know about cosmic strings. The theoretical models are complex, and the experimental evidence is sparse. For now, cosmic strings remain a hypothetical construct, a fascinating idea that may or may not be confirmed through future observations. Yet, even in the absence of direct evidence, the study of cosmic strings has already led to a deeper understanding of the universe and has sparked new ideas that could shape the course of future research. It is this ongoing quest for knowledge that makes the search for cosmic strings so important, as it could hold the key to unlocking some of the most profound mysteries of the cosmos. As technology continues to advance, scientists will have more powerful tools at their disposal to detect and study cosmic strings. From gravitational wave detectors to cutting-edge telescopes, the tools we use to explore the universe are becoming increasingly sophisticated. With each new discovery, we move one step closer to uncovering the secrets of the cosmos, and cosmic strings, should they exist, may play a crucial role in this journey. As we look forward to the future of cosmic string research, one of the most promising developments lies in the study of gravitational waves. Gravitational waves, ripples in space-time caused by massive objects moving or colliding, were first directly detected in 2015 by the LIGO Observatory. These waves are a powerful tool for observing phenomena that are otherwise invisible, and they may hold the key to uncovering the presence of cosmic strings. When two cosmic strings interact, whether they collide or loop around one another, the immense tension involved could produce gravitational waves. These waves would have a distinct signature, potentially differing from those created by black hole mergers or neutron-star collisions. Detecting these specific gravitational wave signatures could provide compelling evidence that cosmic strings are real. In fact, some scientists are currently working on building detectors sensitive enough to pick up these unique signatures, hoping to confirm the existence of cosmic strings. The discovery of gravitational waves from cosmic string interactions could open up an entirely new way to explore the universe. Instead of relying solely on electromagnetic radiation, such as light, radio waves, or X-rays, we could study the universe through gravitational waves, gaining insights into objects and events that have previously eluded us. Cosmic strings, if they exist, may serve as one of the most significant sources of gravitational waves, offering us a fresh perspective on the cosmos and enabling us to test our current theories of physics. Moreover, the study of cosmic strings may offer solutions to some of the biggest puzzles in cosmology, such as the nature of dark matter and dark energy. We already know that these mysterious substances make up most of the universe's mass energy content, yet we have no direct evidence of what they are or how they behave. Some theorists propose that cosmic strings could be linked to these elusive phenomena. For instance, cosmic strings are predicted to possess extremely high energy densities, which could make them a potential candidate for dark matter. If these strings interact with ordinary matter, they could explain some of the strange gravitational effects we observe, such as the way galaxies spin, or the way light bends around massive objects. While dark matter remains invisible to our current instruments, the gravitational influence of cosmic strings might offer a way to detect their presence indirectly. If cosmic strings do, in fact, contribute to the effects attributed to dark matter, it would provide a breakthrough in our understanding of the universe's composition. Similarly, some theories suggest that cosmic strings could have a connection to dark energy, the mysterious force that is causing the accelerated expansion of the universe. If cosmic strings have the ability to warp space-time, they might influence the rate at which the universe is expanding. Understanding how cosmic strings interact with space-time could, therefore, provide valuable insights into the nature of dark energy and the ultimate fate of the universe. Another exciting possibility is that cosmic strings could be the key to understanding the multiverse, the idea that our universe is just one of many. In a multiverse scenario, different universes could exist with different physical laws, and the interactions between them might create ripples in space-time. Cosmic strings could serve as the boundary markers between these universes, or they could be the remnants of collisions between different universes. This idea is still highly speculative, but it presents an intriguing avenue for future research. If cosmic strings could be linked to the multiverse, it would revolutionize our understanding of the cosmos and our place within it. As scientists continue to explore the potential connections between cosmic strings, dark matter, dark energy, and the multiverse, the implications of these discoveries could be far-reaching. It's not just about understanding the mechanics of the universe, but also about redefining the very nature of reality itself. The search for cosmic strings is, at its core, a search for deeper truths about the universe, a quest that could uncover new layers of reality that we have yet to imagine. Moreover, while the theoretical models of cosmic strings are still in their infancy, the potential for discoveries in this area could extend beyond fundamental physics. Understanding the nature of cosmic strings could lead to new technologies, perhaps even offering breakthroughs in fields like energy production or space travel. The idea of tapping into the energy stored in these hypothetical objects, if they exist, could lead to unimaginable advancements in our technological capabilities. For now, that remains a distant dream, but it's a reminder that scientific exploration often leads to unexpected and revolutionary discoveries. For those of us captivated by the mysteries of the universe, cosmic strings represent a thrilling frontier. Whether or not they turn out to be real, the pursuit of knowledge about these objects pushes the boundaries of what we know about the cosmos. It's a testament to the curiosity and imagination that drives scientific inquiry, the drive to answer questions that are so profound and far-reaching that they have the potential to reshape our understanding of the universe. Despite the many unknowns, the search for cosmic strings is a pursuit worth undertaking. As our observational tools become more advanced and our theoretical models become more refined, we may one day uncover the truth behind these cosmic anomalies. If cosmic strings exist, they could provide answers to some of the most profound questions in physics, from the nature of space-time to the origins of the universe itself. And perhaps, more than that, they could offer a glimpse into a reality that is far stranger and more intricate than we ever imagined. While cosmic strings remain theoretical constructs, their potential to unlock new understanding about the universe cannot be overstated. Whether they are remnants of the early universe, sources of dark matter or dark energy, or the keys to understanding the multiverse, these hypothetical objects represent one of the most exciting and mysterious areas of research in modern cosmology. The search for cosmic strings is not just a scientific pursuit. It is a journey to the very heart of the universe's most profound mysteries. Only time will tell if these cosmic anomalies exist, but one thing is certain: the pursuit of knowledge, driven by the questions they raise, will continue to push the boundaries of human understanding. As we continue to explore the nature of cosmic strings, it is important to acknowledge the broader context in which this research is taking place. The field of cosmology, over the past century, has undergone a dramatic transformation, shifting from a passive observation of the universe to an active quest for understanding its most profound secrets. Theories like the existence of cosmic strings are a testament to the power of human imagination, paired with advanced mathematics and observational technology, to push the boundaries of our knowledge. For much of history, our view of the universe was limited by the available technology. Telescopes could only offer us a glimpse of distant stars, and the nature of space itself was largely an abstract idea confined to theoretical musings. However, advancements in technology have changed all of this. Tools such as the Hubble Space Telescope, radio telescopes, and ground-based observatories have revolutionized our understanding of the cosmos. Even more recently, the detection of gravitational waves by LIGO has opened up an entirely new way of observing the universe. These innovations have allowed scientists to probe the farthest reaches of space and time, and they are now helping us investigate phenomena like cosmic strings. The concept of cosmic strings, as strange as it may sound, fits into the broader framework of our attempts to understand the fabric of the universe. Our current theories of the universe, such as general relativity and quantum mechanics, explain much about the behavior of matter, space, and time. However, these theories remain incomplete when it comes to explaining extreme phenomena, such as the origins of the universe or the behavior of particles at the Planck scale. Cosmic strings, as topological defects in space-time, offer a potential bridge between these two realms. At the heart of this quest is the idea that the early universe was not a smooth, uniform place but rather a chaotic, fluctuating environment in which the laws of physics, as we know them, were still taking shape. This is the realm where cosmic strings are thought to have formed. These defects, if they exist, could represent the remnants of that early chaos, a direct connection to the primordial conditions that existed just moments after the Big Bang. The fact that cosmic strings, if they exist, are theorized to be one-dimensional objects adds an additional layer of intrigue to this already fascinating subject. Unlike the familiar three-dimensional objects that we encounter in our daily lives, cosmic strings exist in a higher dimensional space, with their energy stored in an infinitesimally thin line that extends across vast stretches of the cosmos. The idea of such a peculiar object, formed in the very fabric of space-time, is a reminder that the universe operates on a level far beyond our everyday understanding. These strings, with their potential for unimaginable energy and their possible connection to fundamental forces, challenge everything we think we know about the universe. One of the key features of cosmic strings that makes them so tantalizing is their ability to stretch and contract over immense distances, influencing the space around them. This means that, in principle, they could interact with other objects in the universe in ways that would be detectable by scientists. As we've already discussed, gravitational waves might provide a crucial tool for detecting cosmic strings. However, there are also other possible signatures to look for. For example, cosmic strings are thought to possess a unique form of mass. The energy stored within these strings could bend space-time in distinct ways, creating gravitational fields unlike anything we've observed in other objects. This could cause light to bend or objects to move in unexpected ways. The presence of cosmic strings could potentially be inferred by observing how light behaves as it passes through regions of space where these strings might be located. In some models, these strings could even act as cosmic lenses, bending light in such a way that we could detect their presence by analyzing the distortions in distant light sources. It is also worth considering the implications that the discovery of cosmic strings would have on our broader understanding of physics. If cosmic strings are confirmed to exist, they could offer a valuable testing ground for theories that attempt to unify the fundamental forces of nature. One of the biggest challenges in modern physics is reconciling the seemingly incompatible frameworks of general relativity and quantum mechanics. General relativity works incredibly well in explaining large-scale phenomena, such as the behavior of planets, stars, and galaxies, while quantum mechanics excels at explaining the behavior of particles at the microscopic scale. However, these two theories are not easily reconciled, and scientists have been searching for a theory of quantum gravity that can bridge the gap between them. Cosmic strings, as topological defects in space-time, could provide a natural arena in which to test such theories. These objects, which exist at the intersection of both general relativity and quantum mechanics, could serve as a sort of laboratory for understanding how the two theories might come together. By studying the interactions and behaviors of cosmic strings, scientists may be able to unlock new insights into the workings of the universe at both the largest and smallest scales. There is also the possibility that cosmic strings could offer us a glimpse into the nature of the universe beyond our own. Theories of the multiverse suggest that our universe may be just one of many, each with its own set of physical laws. If cosmic strings are connected to the multiverse, as some theorists speculate, they could represent the boundaries between different universes or the remnants of collisions between them. Such an idea is, of course, highly speculative and remains far from proven, but it opens up exciting possibilities for future research. As we continue to delve into the mysteries of cosmic strings, we must also consider the broader implications for our understanding of the universe. The search for these elusive objects is not just about answering a single question, it's about understanding the very fabric of space-time itself. If we can understand how space and time can be warped and manipulated, we might gain insights into the most fundamental processes of the universe, from the birth of galaxies to the nature of black holes. Cosmic strings may not just be theoretical objects, they could be the key to unlocking the next chapter in our quest for knowledge. The search for cosmic strings is more than just an academic exercise, it is a search for the deepest truths about the universe. These hypothetical objects, with their potential to reveal the origins of the universe, the nature of dark matter and dark energy, and even the possibility of a multiverse, represent some of the most exciting frontiers in modern science. Whether or not they exist, the pursuit of cosmic strings is a testament to the power of human curiosity and imagination. As we continue to explore the cosmos, we move ever closer to understanding the fundamental nature of reality itself. And in that pursuit, cosmic strings may prove to be one of the most important and mysterious pieces of the puzzle. As we look to the future, the quest to understand cosmic strings will undoubtedly remain a central focus of cosmological research. Whether through direct detection of gravitational waves, observation of space-time distortions, or theoretical advancements in quantum gravity, scientists will continue to push the boundaries of our knowledge. The mysteries of the universe, once thought to be beyond our reach, are now within our grasp. And in the pursuit of those mysteries, the enigmatic nature of cosmic strings may ultimately reveal the very fabric of space-time itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.